Deep in the universe, there are galaxies so bright that their light could blind entire star systems. But strangely, most of their brilliance is hidden from our eyes, cloaked in thick clouds of cosmic dust. These are hyperluminous infrared galaxies, mysterious giants that glow fiercely in the infrared spectrum, revealing powerful forces at work beneath their dusty veils. What fuels this immense energy? How do these galaxies become so enshrouded, and what do they tell us about the history and future of the cosmos? Join me as we dive into the fascinating and often puzzling world of hyperluminous infrared galaxies, where hidden light tells an extraordinary story. But before we continue, subscribe to the channel so that you don't miss out on any of these videos. Hyperluminous infrared galaxies, or HyLIRGs for short, are the brightest infrared galaxies known in the universe. Their total energy output, especially in the infrared part of the spectrum, is mind-blowing. To put it simply, HyLIRGs can emit more than 1 trillion times the energy of our Sun. That's 1 followed by 12 zeros. These galaxies are so luminous in the infrared that they outshine almost everything else in the sky at those wavelengths. But how do we find something that shines mostly in infrared? It's not as easy as just looking up with a regular telescope. Our eyes and many of our telescopes see visible light, the same kind of light we see with. Infrared light has longer wavelengths, meaning it can pass through dust and gas that block visible light. In fact, HyLIRGs are usually hidden behind thick blankets of dust, which is why their visible light is dim, or even completely blocked. This dust absorbs the light from stars and other sources inside the galaxy, heats up, and then re-radiates that energy as infrared light. So HyLIRGs look dark or faint to us in visible light, but in infrared, they're absolutely blinding. The story of how HyLIRGs were discovered is itself a fascinating chapter in the history of astronomy. Before the 1980s, astronomers didn't really know these kinds of galaxies existed because infrared astronomy was still in its infancy. It wasn't until satellites like the Infrared Astronomical Satellite, IRAS, launched in 1983, that we could scan the entire sky in infrared. IRAS changed everything. It found dozens of galaxies shining with extreme infrared brightness. Among these were what we now call HyLIRGs. They stood out because their luminosity was beyond what could be explained by typical star formation alone. So, what's making these galaxies so hyperluminous? The leading theories point to 2 main sources: intense bursts of star formation and the feeding of supermassive black holes at their centers. Sometimes, it's a combination of both. Let's start with star formation. We know that galaxies form stars all the time, but HyLIRGs are basically star factories on steroids. The star formation rates in these galaxies can be hundreds, or even thousands of times higher than what we see in a normal galaxy like the Milky Way. Imagine entire clouds of gas collapsing and creating new stars at an insane pace, which pumps out huge amounts of ultraviolet and visible light. That light hits the surrounding dust, heats it up, and creates the incredible infrared glow we see. But star formation alone can't explain the full story. Supermassive black holes, millions or even billions of times the mass of our Sun, are often found at the hearts of galaxies. When a black hole actively gobbles up gas and dust, it forms what's called an active galactic nucleus, or AGN. These AGNs release enormous amounts of energy, often more than all the stars in their host galaxy combined. In HyLIRGs, these AGNs are thought to be heavily hidden inside thick dust clouds, which block visible light but allow infrared light to escape. In many HyLIRGs, the energy output from the AGN and the intense star formation feed into each other, creating an explosive feedback loop. Gas falling into the black hole powers the AGN, which can then blow out winds and radiation that compress nearby gas clouds, triggering even more star formation. Or it might blow gas away, eventually shutting down star formation. The details are complex and still under active study, but it's clear that these processes shape how HyLIRGs evolve. One of the most amazing things about HyLIRGs is their role in the history of the universe. Most HyLIRGs we detect are very far away, meaning their light has traveled billions of years to reach us. We're seeing them as they were in the early universe, only a few billion years after the Big Bang. This tells us HyLIRGs were more common when the universe was young and active. Back then, galaxy collisions were much more frequent. These collisions can smash gas clouds together, triggering the intense starbursts and AGN activity that give birth to HyLIRGs. So HyLIRGs help us understand a crucial phase of galaxy formation and evolution. They're snapshots of the wild teenage years of galaxies when star formation and black hole growth were at their peak. Eventually, these galaxies calm down, lose their dust, and evolve into the quieter galaxies we see today. Studying HyLIRGs also challenges our models of how galaxies grow. Some HyLIRGs are more massive than expected, and their intense energy output raises questions about how they accumulate and retain so much gas without blowing it all away. These puzzles push astronomers to rethink the physics of gas dynamics, star formation, and black hole feeding on cosmic scales. Modern telescopes are opening new windows into HyLIRGs. Instruments like the Spitzer Space Telescope and now the James Webb Space Telescope, JWST, are revealing their detailed structures and environments. JWST's powerful infrared cameras let us see the dust-enshrouded regions in stunning detail, tracing the heating sources and star formation regions. These observations help us map where stars form, how gas moves, and how AGNs interact with their surroundings. One of the most exciting recent discoveries is the diversity among HyLIRGs. Not all of them look or behave the same. Some are dominated by starbursts, others by AGNs, and many show a mix of both. Some seem to be merging galaxies, while others are giant isolated systems. This variety hints that HyLIRGs might represent different stages or types of galaxy evolution rather than one single class. The mystery deepens when we think about what happens next. After these hyperactive phases, galaxies often lose much of their gas and dust, possibly due to powerful winds driven by the AGN or star formation. This shuts down star formation and leaves behind massive, quiet galaxies. But the exact mechanisms and timelines are still uncertain, making HyLIRGs a key focus for understanding how galaxies grow up. Also fascinating is the connection between HyLIRGs and other mysterious objects in the universe, like quasars, extremely bright AGNs that shine mostly in visible and ultraviolet light. Some astronomers believe HyLIRGs are the dust-hidden predecessors of quasars. As the dust clears, the galaxy might shift from being a hyperluminous infrared galaxy to a quasar, revealing the powerful black hole at its center. In short, hyperluminous infrared galaxies are cosmic beasts unlike any others. They are some of the most energetic and mysterious objects in the universe, shining brilliantly in the infrared while hiding secrets behind thick veils of dust. They tell stories about how galaxies formed in the early universe, how stars and black holes grow, and how the most extreme environments shape cosmic evolution. If we want to fully understand how the universe grew from a hot, simple state after the Big Bang to the complex collection of stars, planets, and galaxies we see today, we have to unlock the secrets of HyLIRGs. They are keys to the cosmic puzzle of galaxy formation and evolution, still challenging our knowledge and inspiring new questions. Now you might be thinking, that's incredible, but how do astronomers actually study these hidden giants? What techniques and tools are used to peer through the dust and uncover their secrets? That's where technology and science meet in fascinating ways. Infrared telescopes, both in space and on Earth, use sensitive detectors to catch the faint glow from dust. Spectroscopy allows scientists to break down this light and analyze what it's made of, revealing clues about the temperature, composition, and motion of the dust and gas. Ground-based observatories equipped with adaptive optics can see sharper images of HyLIRGs by compensating for Earth's atmospheric turbulence. Radio telescopes can also detect signals from molecules in the gas clouds, giving insights into star formation and the impact of black holes. Each new observation helps build a clearer picture. Scientists combine data from different wavelengths, radio, infrared, optical, X-ray, to understand all the physical processes at play. This multi-wavelength approach is crucial because no single kind of light tells the full story. Another exciting aspect is how HyLIRGs fit into the bigger cosmic web. They are often found in dense regions of the universe, where galaxies cluster and interact more frequently. Studying their environments sheds light on how large-scale structure influences galaxy growth and evolution. Understanding HyLIRGs also impacts our knowledge of cosmology, the study of the universe's origin, structure, and fate. Their brightness helps astronomers measure distances and map the universe's expansion. Their numbers and properties over time provide clues about how matter clumped together to form galaxies. Despite all the progress, many mysteries remain. For instance, what exactly triggers the sudden bursts of star formation in HyLIRGs? Are galaxy collisions always involved, or can internal processes cause these explosions? How do the black holes grow so quickly to reach supermassive sizes in such a short cosmic time? How does the dust survive the intense radiation and winds inside these galaxies? As technology improves and new telescopes come online, scientists are hopeful they'll uncover answers. The James Webb Space Telescope is already making waves, and future missions will push even further. The universe is full of wonders, but few are as fascinating or as challenging as hyperluminous infrared galaxies. These cosmic giants hide behind dust and glow with the power of trillions of suns, telling us about the wild youth of galaxies, the fierce battles between stars and black holes, and the shaping forces of cosmic evolution. As we keep searching and learning, HyLIRGs remind us how much there still is to discover in the vast expanse of space. To understand HyLIRGs better, it helps to zoom out and look at the bigger picture of galaxy types and infrared astronomy. Galaxies come in many shapes, sizes, and brightness levels. Most of the galaxies we see with regular telescopes shine primarily in visible light. Spiral galaxies like our Milky Way have plenty of stars emitting that light. Elliptical galaxies, which tend to be older and less active, can look smoother and less colorful because they have fewer young stars. But HyLIRGs don't play by these usual rules. They belong to a special family of galaxies known as infrared luminous galaxies. These are galaxies that shine more brightly in the infrared than in visible light, usually because of large amounts of dust. The dusty clouds inside absorb visible and ultraviolet light, then re-radiate it as infrared radiation. Within this family, HyLIRGs are at the extreme end of brightness. They are even brighter than ultraluminous infrared galaxies, HyLIRGs, which themselves are already some of the most active and bright galaxies known. To understand HyLIRGs, it helps to understand HyLIRGs first. HyLIRGs often result from galaxy mergers, two or more galaxies smashing together. This collision throws gas and dust clouds into chaos, compressing them and triggering massive bursts of star formation. The chaos also fuels the central supermassive black hole, turning it into an active galactic nucleus, AGN. HyLIRGs can emit about 100 billion to a trillion times the sun's luminosity in infrared. HyLIRGs are even more luminous, pushing beyond that trillion solar luminosity mark. The difference is partly scale but also physical processes. HyLIRGs tend to be more distant, representing an earlier universe when galaxy collisions and starbursts were more common and intense. The larger amount of dust and gas also means the visible light is almost entirely hidden, making HyLIRGs some of the most challenging objects to study. Because HyLIRGs are so distant and shrouded in dust, their discovery was limited until we developed sensitive infrared observatories. IRAS, as mentioned earlier, was the first all-sky survey in the infrared and revolutionized the field. Later missions like the Infrared Space Observatory, ISO, the Spitzer Space Telescope, and now JWST have added incredible detail. These telescopes don't just see the glow, they can take spectra, splitting the infrared light into its component wavelengths. This reveals the chemical fingerprints of molecules in the dust and gas, the temperature of the dust, and even the motion of gas clouds within the galaxy. One of the chemical clues is the presence of polycyclic aromatic hydrocarbons, PAHs, complex carbon molecules that are common in star-forming regions. PAHs tend to be destroyed by intense radiation from AGNs, so their presence or absence helps astronomers decide whether star formation or black hole activity dominates the galaxy's energy output. Another important diagnostic tool is the shape of the infrared emission spectrum. Starbursts tend to produce a certain signature spectrum because the dust is heated by many hot, young stars. AGNs, however, produce a hotter dust component and sometimes show emission lines from highly ionized gas near the black hole. The balance of these features in HyLIRG spectra often reveals a complex mix of processes. Many HyLIRGs seem to be composite systems, with both strong starburst activity and powerful AGNs. Studying HyLIRGs also involves looking at their host galaxies' morphology, their shapes and structures. Many HyLIRGs show signs of interactions or mergers, like tidal tails, distorted shapes, or double nuclei. These are strong clues that the hyperactivity comes from galaxies crashing together and mixing their gas and dust. The big question is what triggers such extreme luminosities. In many cases, it's thought to be major galaxy mergers. When two large galaxies collide, their gas clouds can lose angular momentum and funnel toward the center, feeding starbursts and the central black hole. The dust created by massive stars or expelled from the central AGN can then trap light, creating the hyperluminous infrared glow. However, some HyLIRGs show signs of being very massive, isolated systems, suggesting that extreme luminosity can also come from rapid gas accretion in the early universe or other processes. Another fascinating topic is how HyLIRGs fit into the life cycles of galaxies. The universe is about 13.8 billion years old, and galaxies have evolved tremendously during that time. Early in the universe's history, about 10 to 12 billion years ago, star formation rates were much higher on average, and galaxy mergers more frequent. HyLIRGs seem to represent a brief but intense phase during this epoch. After a hyperluminous phase, feedback from AGNs or supernovae, explosions from dying stars, can blow away the dust and gas, quenching star formation. This can leave behind a massive, red and dead, elliptical galaxy, dominated by older stars and little ongoing star formation. So HyLIRGs might be the teens of galaxies, wild and chaotic, before settling into mature adulthood. This life cycle idea helps explain why we see fewer HyLIRGs nearby. They mostly existed when the universe was younger. The study of HyLIRGs also ties into the cosmic infrared background radiation, a faint glow filling the universe in infrared light, thought to come from countless distant, dusty galaxies like HyLIRGs and HyLIRGs. Understanding HyLIRGs helps us explain the origin and makeup of this background, which is important for understanding cosmic evolution. Looking ahead, there are huge opportunities for discovery. The JWST, with its advanced infrared detectors, is already revealing new HyLIRGs at greater distances and with more detail than ever before. It can even peer back to when the first HyLIRGs formed, shedding light on how the earliest massive galaxies grew. Next-generation ground telescopes, like the Extremely Large Telescope, ELT, and the 30-meter telescope, TMT, will provide unprecedented resolution and sensitivity to study HyLIRGs' detailed structures and star formation regions. In addition, new instruments for radio and sub-millimeter wavelengths, such as ALMA, ATACM, a large millimeter/sub-millimeter array, allow astronomers to trace cold gas and dust with incredible precision. This gives insight into the raw material feeding star formation and black holes. All of these advances mean the coming decades could revolutionize our understanding of HyLIRGs and their role in the universe. The mysteries are deep and the questions big. How do supermassive black holes grow so fast? How exactly do starbursts ignite and then get shut down? Why do some HyLIRGs have more AGN activity while others are starburst dominated? Are there HyLIRGs even more luminous or massive than we've found so far, hidden deeper in the cosmic dust? Could HyLIRGs influence their surrounding environment on huge scales, affecting the formation of galaxy clusters or even the large-scale structure of the universe? To put it simply, hyperluminous infrared galaxies are cosmic laboratories where some of the most extreme and energetic processes in the universe play out. They push the boundaries of astrophysics and cosmology, forcing scientists to rethink ideas about galaxy growth, star formation, black hole physics, and cosmic history. For anyone fascinated by the cosmos, HyLIRGs offer a thrilling glimpse into the wild, energetic, and dusty corners of space where galaxies blaze fiercely, hidden behind veils of cosmic dust. And as we continue to improve our technology and reach further back in time, we can only imagine the new secrets these cosmic giants will reveal, secrets that might reshape our understanding of how the universe became the place we live in today. One of the key puzzles around HyLIRGs is their connection to supermassive black holes. Almost every massive galaxy has a supermassive black hole at its center, but HyLIRGs take this to a whole new level. In many HyLIRGs, the central black hole is actively feeding, pulling in huge amounts of gas and dust, and releasing massive energy in the process. This active feeding phase is called an active galactic nucleus, or AGN for short. The energy released by AGNs can outshine the combined light of all the stars in the galaxy, but because of the dense dust around them in HyLIRGs, much of this energy is absorbed and re-emitted as infrared light. That's why these galaxies appear so bright in the infrared spectrum but are often invisible or faint in visible light. Scientists are particularly interested in how these black holes grow so quickly and how they interact with their host galaxies. For instance, as the black hole gobbles up material, it also pumps out powerful winds and jets of particles that can push away gas and dust. This process is called feedback, and it can regulate or even shut down star formation in the galaxy. Feedback is a major piece of the puzzle. It might explain why galaxies stop forming stars and evolve into quieter, older galaxies. But in HyLIRGs, this feedback is in full throttle. The question is how this feedback balances with the extreme star formation happening at the same time. Is the black hole trying to choke off the star formation, or do the stars and black holes somehow grow together in a delicate dance? To add to the mystery, some HyLIRGs seem to host not one but multiple black holes, likely because they formed from galaxy mergers that combine two or more black holes into one system. This can create extremely complex gravitational dynamics, leading to phenomena like black hole binaries or even triple systems. These black hole mergers are important for another reason too. When two supermassive black holes spiral together and merge, they release powerful gravitational waves, ripples in spacetime, that can travel across the universe. Detecting these gravitational waves from supermassive black holes is one of the biggest goals in astronomy today, and HyLIRGs could be promising sites where these events happen. Aside from black holes, HyLIRGs are also fascinating for their star formation. The rate of star birth in some HyLIRGs can be thousands of times higher than in the Milky Way. Imagine that, creating thousands of stars every year, each one potentially hosting its own planetary system. The environments in HyLIRGs are extreme, with intense radiation fields, strong stellar winds, and turbulent gas clouds. Because of all this, HyLIRGs offer a natural laboratory to study how stars form under conditions very different from those in calmer galaxies like ours. Understanding star formation in these galaxies could tell us a lot about how the earliest stars formed in the young universe. One way scientists study star formation is by looking at molecular gas, mostly hydrogen molecules, which are the raw material for making stars. In HyLIRGs, this gas is dense, turbulent, and often heated by radiation from stars and black holes. Using powerful radio telescopes like HyLIRGs, astronomers can map the distribution and movement of this gas in great detail, seeing where new stars are likely forming and how the gas flows through the galaxy. Another key mystery is the role of dust in HyLIRGs. Dust grains are tiny particles made mostly of carbon and silicon, but they have an outsized effect on how we see galaxies. In HyLIRGs, dust absorbs ultraviolet and visible light and re-radiates it as infrared, but it also affects the chemistry and cooling of the gas, influencing star formation. The composition and properties of dust in HyLIRGs can differ from those in less active galaxies. Studying this dust can tell us about the life cycles of stars, since dust is created and destroyed in supernova explosions and stellar winds, and about how galaxies recycle their material. Because HyLIRGs are so distant, studying them also helps us understand the universe's history. Light from the farthest HyLIRGs has taken billions of years to reach us, so we see them as they were when the universe was much younger. This lets astronomers study the peak era of galaxy formation and black hole growth, giving clues about how the cosmos evolved. The more we observe HyLIRGs at different distances, the better we understand how common these hyperluminous phases were and how galaxies changed over time. Another intriguing aspect is whether HyLIRGs are a single phase in galaxy evolution or if there might be different pathways to becoming hyperluminous. Some evidence suggests HyLIRGs can arise not only from galaxy mergers but also from rapid gas accretion in very massive dark matter halos, or from dense groups of smaller galaxies interacting. The diversity among HyLIRGs is still being explored. Some HyLIRGs show very strong AGN signatures, while others are dominated by starbursts. Some look like merging systems, while others appear more relaxed. This diversity hints at a complex set of physical processes and environmental factors shaping these galaxies. HyLIRGs are also important for cosmology because they help explain the buildup of stellar mass and heavy elements, metals, in the universe. The intense star formation in HyLIRGs means they're major factories for producing heavier elements like carbon, oxygen, and iron, which are essential for forming planets and life as we know it. By studying the metal content of HyLIRGs and how it changes with redshift, distance, astronomers can trace how chemical enrichment proceeded through cosmic time. Despite all these discoveries, many questions remain. How do the extreme environments in HyLIRGs affect planet formation? Could some of these hyperactive galaxies host early planetary systems? How do magnetic field shape gas dynamics in HyLIRGs? And how does the interplay of gravity, radiation, and feedback regulate their evolution? As technology advances, we expect answers to come from new observatories like JWST, ELT, and the next generation of radio and millimeter arrays. These tools will offer sharper images, deeper spectra, and more precise measurements to probe HyLIRGs' internal structure and their environments. But even beyond these instruments, HyLIRGs remind us how much remains unknown about the universe. They challenge our theories and invite us to imagine extremes of nature, galaxies glowing with the light of a trillion suns, hidden behind thick veils of dust, at the edge of the observable universe. In many ways, studying HyLIRGs is a journey to the universe's most intense and hidden fireworks, revealing the cosmic drama of galaxy birth, growth, and transformation in ways few other objects can. And so, the story of hyperluminous infrared galaxies is far from over. Each new observation peels back a little more of the mystery, but also opens new questions. They are a reminder that even in a universe we think we understand, there are still places where nature's power runs wild, and our curiosity has no limits. One fascinating area of research is the role that cosmic environment plays in shaping HyLIRGs. We know galaxies don't live in isolation. They're part of larger structures called galaxy clusters and superclusters, massive cosmic webs of matter stretching millions of light years. The environment can influence how galaxies evolve by affecting the supply of gas available for star formation and feeding their central black holes. In dense environments, galaxies are more likely to collide and merge, which can trigger the hyperluminous phases we see in HyLIRGs. These violent interactions funnel gas toward the galaxy centers, igniting furious starbursts and feeding the black holes. So, HyLIRGs may preferentially form in regions where galaxies crowd together. But intriguingly, some HyLIRGs appear in less crowded regions too, hinting that other processes can also fuel their intense activity. Perhaps rapid inflows of cold gas from the cosmic web can sustain star formation and black hole growth without mergers. Understanding this balance between mergers and gas accretion in different environments helps clarify the cosmic history of galaxy assembly. Next, the shapes and structures of HyLIRGs are a treasure trove of information. Many HyLIRGs are highly disturbed, with tidal tails, loops, and irregular shapes, classic signs of galaxy collisions. These tell us the story of their violent pasts. Others, however, show surprisingly regular shapes, maybe disks or ellipses, suggesting a quieter evolution or that they are caught at different stages in the hyperluminous phase. Some astronomers use high-resolution imaging with telescopes like the Hubble Space Telescope or the JWST to look at HyLIRGs in exquisite detail. This allows them to see whether the light comes from a compact core, an extended star-forming region, or multiple nuclei from merging galaxies. Each of these tells a different story about how the galaxy formed and what's powering its luminosity. Another mystery tied to HyLIRGs is their link to quasars, some of the brightest, most energetic objects in the universe. Quasars are also powered by accreting supermassive black holes, but they shine most brightly in visible and ultraviolet light, often outshining their host galaxies. HyLIRGs might be the dusty, obscured ancestors or cousins of quasars. In other words, some astronomers think HyLIRGs represent a phase where the black hole is growing behind thick curtains of dust before it eventually blows the dust away and reveals itself as a quasar. This evolutionary link between HyLIRGs and quasars is a hot topic because it ties together star formation, black hole growth, and galaxy transformation in a unified picture. But this model is still debated. Some HyLIRGs may never become quasars, and others may follow different evolutionary paths. Moving to the cosmic timeline, The peak of HyLIRG activity seems to be several billion years ago, roughly 10 to 12 billion years back in time, during a period known as cosmic noon. This was when the universe was at its most active, with galaxies rapidly forming stars and black holes growing fast. Studying HyLIRGs from this epoch lets us glimpse a crucial phase in cosmic history when many of today's galaxies took shape. However, HyLIRGs have been found across a range of distances and ages, suggesting that these intense bursts of activity can happen at different times and perhaps under different conditions. Something else that adds to the mystery is the diversity of the infrared emission itself. Infrared light covers a range of wavelengths, from near-infrared to far-infrared and sub-millimeter. Different parts of this spectrum can come from different sources inside the galaxy: warm dust heated by young stars, very hot dust near the black hole, or even cold dust far from the core. By studying the infrared spectral energy distribution, basically, how the brightness changes with wavelength, astronomers can disentangle these different components. This is important to estimate how much of the luminosity comes from star formation versus the black hole, and to understand the dust properties. In some HyLIRGs, the far-infrared emission is dominant, suggesting starbursts produce most of the energy. In others, the mid-infrared shines brightest, hinting at a dominant active black hole. But many HyLIRGs have a mix of both, making them complex systems where stars and black holes grow side by side. Then there's the question of gas dynamics inside HyLIRGs. Observations reveal that gas clouds in these galaxies can be moving at hundreds, or even thousands of kilometers per second. Some gas is inflowing, feeding the central black hole or star formation, while other gas is being blown out in powerful winds. These outflows can be driven by radiation pressure from the black hole or from the collective effects of many supernova explosions from massive stars. Such winds can sweep away gas and dust, regulating or ending star formation and black hole growth. Measuring these outflows and their impact is essential for understanding the life cycle of HyLIRGs and how galaxies evolve from active star-forming objects to more passive ones. We also can't forget about magnetic fields, which are harder to detect but could play a significant role in shaping the gas dynamics and star formation in HyLIRGs. Magnetic fields can influence how gas collapses to form stars and how jets and winds propagate. Another angle of study is the connection between HyLIRGs and cosmic dust production and destruction. Dust grains are formed in the envelopes of dying stars and supernovae, but they can also be destroyed by shocks and intense radiation. HyLIRGs, with their extreme environments, are perfect laboratories to study these processes, which impact how galaxies recycle their material. Studying HyLIRGs also helps astronomers calibrate the cosmic infrared background, the glow of accumulated infrared light from all galaxies throughout cosmic history. HyLIRGs contribute a significant part of this background because of their brightness in the infrared. Understanding this background sheds light on the total star formation and black hole growth across the universe. There's the role of HyLIRGs in the context of dark matter and large-scale cosmic structure. These galaxies reside in massive dark matter halos that shape their formation and evolution. Mapping HyLIRGs and their environments helps trace the distribution of dark matter and understand how galaxies populate the cosmic web. HyLIRGs are not just bright galaxies. They are cosmic laboratories where the most intense processes of star formation, black hole feeding, dust creation, and gas dynamics come together in a dramatic, often violent way. They challenge our understanding of how galaxies grow and evolve and offer a window into the most energetic phases of the universe's history. With new telescopes and instruments coming online, the future is bright for HyLIRG studies. These cosmic giants will keep surprising us and pushing the boundaries of what we know about the universe. One of the most exciting frontiers in studying HyLIRGs is using new technology like the James Webb Space Telescope. This telescope has incredible sensitivity in the infrared, which is perfect for peering through the thick dust clouds that usually hide HyLIRGs from view. JWST allows astronomers to see the detailed structure inside these galaxies for the first time, mapping out where stars are forming and where the black hole is feeding. This helps answer questions that have lingered for decades, such as how these galaxies can be so bright yet so hidden at the same time. Along with JWST, powerful ground-based observatories equipped with advanced instruments are helping to measure the gas and dust properties in HyLIRGs with more precision. Radio telescopes like ALMA, ATACM, a large millimeter/submillimeter array, can detect cold molecular gas, the raw material for star formation, in distant galaxies. By observing HyLIRGs in radio and submillimeter wavelengths, astronomers can estimate how much fuel these galaxies have left to keep forming stars and growing their black holes. This kind of data is key to understanding how long the hyperluminous phase lasts, and what might trigger it to end. Another tool in this quest is spectroscopy, which breaks down the light from these galaxies into its component colors or wavelengths. Spectroscopy reveals the chemical fingerprints of elements and molecules in the gas and dust. By analyzing these, scientists can learn about the conditions inside HyLIRGs: temperature, density, speed of gas movements, and the history of star formation and black hole activity. It also allows them to measure redshifts, confirming how far away these galaxies are and how long ago their light was emitted. HyLIRGs also connect to the bigger picture of galaxy evolution. Most galaxies in the nearby universe are relatively calm, with modest star formation rates. But billions of years ago, the universe was a wild place where galaxies like HyLIRGs were common. Understanding HyLIRGs helps fill in the gap between those early chaotic times and today's calmer universe. One idea is that HyLIRGs might represent a critical transformation phase. A normal galaxy might undergo a violent event, like a collision, that triggers a burst of star formation and black hole feeding, turning it into an HyLIRG. Eventually, the energy output and winds from the black hole blow away the dust and gas, stopping star formation and leaving behind a quasar or an elliptical galaxy. This life cycle model links different types of galaxies into a continuous story of birth, growth, and change. However, not all HyLIRGs fit neatly into this picture. Some seem to be in different evolutionary stages or might be powered by different mechanisms. The diversity among HyLIRGs hints that there might be multiple paths to becoming hyperluminous, depending on factors like environment, galaxy mass, and the availability of gas. Researchers also look at the connection between HyLIRGs and galaxy clusters. These massive structures contain hundreds or thousands of galaxies bound by gravity. HyLIRGs found in clusters might have their evolution influenced by the cluster environment, such as increased chances of collisions or gas stripping from interactions with the hot intra-cluster medium. Comparing HyLIRGs inside clusters with those in more isolated areas reveals how environment affects galaxy growth. In terms of cosmology, HyLIRGs help refine our understanding of how the universe builds structure over time. They trace regions of intense activity where matter collects and stars form rapidly. By studying the distribution and properties of HyLIRGs across cosmic time, astronomers can test models of dark matter, cosmic expansion, and galaxy formation. HyLIRGs also raise questions about the initial conditions that allow such extreme activity. For example, what kinds of galaxies are most likely to become HyLIRGs? Is it mainly massive galaxies with abundant gas, or can smaller galaxies also undergo this phase? How do the masses of their central black holes compare to their host galaxies? And how does this ratio change over time? The feedback mechanisms from HyLIRGs are another major puzzle. The powerful winds and radiation they produce can shape the surrounding intergalactic medium, influencing the formation of nearby galaxies. This feedback is a crucial ingredient in simulations of galaxy formation, but it is difficult to model accurately because of the complex physics involved. Some HyLIRGs show signs of jets, streams of high-energy particles launched from near the black hole at nearly the speed of light. These jets can extend for thousands of light years, impacting the galaxy's gas reservoir and even the larger cosmic environment. The interaction between jets and the gas can either trigger new star formation by compressing clouds or suppress it by heating and expelling the gas. The presence or absence of jets and their impact on HyLIRGs is an area of active study. Understanding how these jets form and evolve is linked to the spin of the black hole and the magnetic fields threading the accretion disk. HyLIRGs also help probe the nature of dust in the early universe. Dust plays a key role in cooling gas clouds, enabling star formation, but its origin and evolution in galaxies with extreme activity are still not fully understood. Observations suggest that dust in HyLIRGs is often produced rapidly, perhaps from supernovae explosions, but it also undergoes processing in the harsh environments near black holes. The composition, size distribution, and temperature of dust grains affect how galaxies emit light, and modeling this emission helps interpret observations across multiple wavelengths. Understanding dust properties in HyLIRGs can also shed light on how dust affects galaxy observations in general, including biases in surveys that look for star-forming galaxies. HyLIRGs may also host massive star clusters and superstar clusters, which are groups of stars born together in intense bursts. These clusters can contain thousands to millions of stars packed into a small volume and are important laboratories for studying how stars form in extreme conditions. Observing these clusters inside HyLIRGs can reveal how star formation proceeds when the galaxy is undergoing a hyperluminous phase. Furthermore, HyLIRGs provide clues about the formation of the most massive black holes. Since HyLIRGs host rapidly growing black holes, they offer a way to understand how black holes reach billions of times the mass of the Sun within a relatively short time after the Big Bang. This is a major question in astrophysics, as it challenges our understanding of black hole growth rates and seed black hole formation. HyLIRGs also intersect with studies of gravitational waves, as the merging of galaxies and black holes can produce ripples in spacetime detectable by instruments like LIGO and Virgo. Although direct gravitational wave signals from HyLIRGs have not yet been observed, future detectors could potentially pick up these signals, giving us a new way to study these energetic systems. The complexity of HyLIRGs makes them challenging but rewarding targets for theoretical modeling and numerical simulations. Computer simulations try to recreate the formation and evolution of HyLIRGs by including physics like gravity, gas dynamics, star formation, black hole accretion, and feedback processes. These simulations help test hypotheses and interpret observations but require significant computing power and detailed physics. Overall, HyLIRGs are among the most extreme and fascinating objects in the universe. They challenge our understanding of how galaxies and black holes grow, how dust and gas behave in extreme environments, and how cosmic structures evolve over billions of years. Each new discovery about HyLIRGs opens new questions, making them an endless source of mystery and wonder. Because HyLIRGs push the boundaries of what galaxies are capable of, they sit at the very edge of our cosmic understanding. They don't just emit more light than other galaxies, they emit more light than entire clusters of galaxies combined. And yet that light is mostly hidden, cloaked behind thick blankets of cosmic dust. What we see is only what manages to leak through or irradiate in the infrared. It's like trying to understand the workings of a volcano by watching smoke seep out of cracks in a mountain from miles away. But even from that smoke, we know something immense is going on. This is where the importance of multi-wavelength astronomy comes into play. HyLIRGs aren't visible in the same way regular galaxies are. Optical telescopes, the kind that see the same wavelengths as our eyes, are practically blind when it comes to detecting these objects. They need to be hunted down using infrared, radio, and submillimeter instruments. When scientists finally spot one, they begin layering observations from across the electromagnetic spectrum to build a complete picture. It's like solving a puzzle where each color of light provides a different set of clues. What's truly puzzling about HyLIRGs is how quickly they appear and how fast they burn through their energy. In cosmic terms, most galaxies take their time. Star formation can last billions of years. But HyLIRGs seem to go through their resources in a cosmic flash, forming hundreds or thousands of solar masses worth of stars each year. That's like trying to grow an entire forest overnight. This wild pace raises questions about what sets off such an extreme phase and how it can be sustained. One theory is that HyLIRGs represent a temporary, blowout, stage. This is when a galaxy's black hole and star formation activity hit their peak at the same time, pumping out huge amounts of energy until it becomes too much for the galaxy to handle. Eventually, winds from supernovae and jets from the black hole push out the gas and dust, shutting down further activity. The galaxy dims, the starburst ends, and what's left is a quieter system, possibly a massive elliptical galaxy or a luminous quasar. But there are outliers. Some HyLIRGs show evidence of being in this phase for surprisingly long periods. That suggests either that they are continuously supplied with fresh gas, perhaps from cosmic filaments or smaller mergers, or that their feedback mechanisms are not as effective as we think. If they can somehow keep the engine running, That might explain how some of the largest black holes in the universe grew so quickly. HyLIRGs are also important for understanding the timeline of the early universe. When we observe one, especially at a high redshift, we're seeing light that has traveled for billions of years. That means we're not just looking far away, we're looking back in time. And if we're seeing a hyperluminous phase in a galaxy just a few 100 million years after the Big Bang, that tells us that massive galaxies, intense star formation, and powerful black holes were already in full swing very early in the universe's history. This forces astronomers to rethink models of galaxy formation. Traditionally, the early universe was thought to be a slow build, small structures merging into bigger ones over time. But HyLIRGs suggest that some galaxies skip the line, growing rapidly and forming stars at rates that are hard to explain with conventional theories. They might be the cosmic equivalents of teenage prodigies, burning bright, burning fast, and defying expectations. Even the chemical composition of HyLIRGs is strange. In many of them, we see metals, elements heavier than hydrogen and helium, at levels that imply multiple generations of stars have already lived and died. But how could that be, if these galaxies are so young? One possibility is that star formation in HyLIRGs is incredibly efficient and occurs in compact, dense environments where stars form, die, and enrich the surrounding gas in rapid succession. But these environments are also chaotic. Inside an HyLIRG, radiation pressures are enormous. Supernova explosions light up like constant fireworks. Magnetic fields twist and snap. Dust grains form and are destroyed almost as quickly. It's like watching a factory run at 1000% capacity, every machine redlining, every process pushed to the extreme. And yet these systems somehow hold together, at least for a time. There's also a curious link between HyLIRGs and gamma-ray bursts. These bursts, which are the most energetic explosions in the universe, often occur in distant galaxies with active star formation. Some theories suggest that HyLIRGs might be breeding grounds for the kinds of massive stars that eventually go supernova and produce gamma-ray bursts. If this is true, then HyLIRGs are not just bright, they're deadly. They are producing stars that live fast, die young, and go out with a bang that can outshine an entire galaxy for a few seconds. HyLIRGs may also be connected to the cosmic infrared background. This background radiation is the sum total of all the infrared light emitted by galaxies throughout cosmic history. Because HyLIRGs are such prolific emitters in the infrared, they likely contribute a significant portion to this background. By studying them, we gain insight into the universe's hidden energy budget, the light that isn't visible but is still there, whispering secrets from the past. One unexpected twist is the idea that we may have missed many HyLIRGs. Since they are so dust-obscured, it's possible that even with modern surveys, we're only seeing the tip of the iceberg. New generations of infrared observatories, especially space-based ones that avoid Earth's atmosphere, are expected to uncover far more. These discoveries could dramatically increase our understanding of how common HyLIRGs are and how they fit into the larger cosmic web. And speaking of that web, HyLIRGs are not isolated phenomena. They tend to occur in dense environments, the knots and filaments of the cosmic structure where matter is concentrated. Studying their spatial distribution can reveal how large-scale structures in the universe influence galaxy behavior. Are HyLIRGs the natural outcome of galaxies colliding in crowded neighborhoods? Or do they form in isolation, only later to migrate into more populated regions? What makes HyLIRGs even more interesting is their role in feedback processes. The energy they release doesn't stay confined to the galaxy. It pushes out into the intergalactic medium, heating gas, driving shocks, and altering the physical state of the surrounding universe. This means HyLIRGs are not just shaped by the cosmos, they help shape it in return. They're players in the grand narrative, not just background characters. Their outflows, in particular, are a focus of research. These winds can move at thousands of kilometers per second and carry more mass than entire stars. When they slam into surrounding gas, they can strip it away, preventing new stars from forming. But under the right conditions, they can also compress gas clouds, triggering new star formation elsewhere. This dual nature, destructive and creative, adds another layer of mystery. HyLIRGs also test the limits of our simulation technology. Creating accurate models of galaxies that form stars this rapidly, and contain such powerful black holes is challenging. It requires simulating millions or billions of particles and taking into account gravity, hydrodynamics, radiation pressure, magnetic fields, chemical reactions, and relativistic physics. Even then, small errors can compound quickly, making it difficult to match simulations with observations. Some HyLIRGs are now being targeted for detailed case studies. By focusing on a single galaxy and collecting data across all wavelengths and instruments, scientists can piece together its story, when it formed, how it evolved, what triggered its hyperluminous phase, and how it might end. These individual stories, when added together, help form a larger picture of cosmic evolution. And that's where the real beauty of HyLIRGs lies. They are cosmic time capsules. Each one holds clues to the state of the universe billions of years ago, preserved in the light that's only now reaching us. They are a reminder that even in the darkness of space, hidden behind dust and distance, galaxies are waging fierce battles of creation and destruction, lighting up the cosmos in ways we are only just beginning to understand. And as we peer deeper into these galactic giants, another surprising realization emerges. HyLIRGs challenge what we thought was possible in terms of energy production in the universe. Think about it. For a galaxy to shine with more than 100 trillion times the brightness of our Sun, and to do so not briefly, but over extended periods, suggests a kind of cosmic engineering that we still don't fully grasp. These aren't just big versions of normal galaxies. They are something fundamentally different, more intense, more chaotic, more extreme. Astronomers often measure a galaxy's luminosity by calculating its infrared output, especially when dust obscures much of the optical light. HyLIRGs don't just top the charts, they break the scale. They occupy a rare, almost mythical tier of brightness. Many of them were first discovered not through traditional telescopes, but by infrared surveys like IRES, Herschel, and Spitzer, instruments that could pick up the intense glow of warm dust. These galaxies weren't visible before because we simply weren't looking in the right part of the spectrum. And that raises a provocative question. How many HyLIRGs have gone unnoticed because we weren't looking in the right way? We've only scratched the surface of what's out there. With instruments like the James Webb Space Telescope, which specializes in infrared detection, we're beginning to discover just how crowded the hidden universe might be. Webb's deep field surveys are already uncovering dusty galaxies that were invisible before. Many of these could be HyLIRGs or related systems, showing us that the cosmos is far more active in the infrared than we once believed. But here's where things get even weirder. HyLIRGs don't all look the same. Some appear to be undergoing massive mergers, galaxies colliding, their gas and stars thrown into a frenzy, triggering extreme starbursts. Others seem more stable, with central engines, likely supermassive black holes, dominating the energy output. This diversity suggests that hyperluminous is a condition, not a single recipe. Multiple paths can lead to this level of brightness. Some are driven by gravity pulling galaxies together. Others may be fueled by accretion disks spinning around hungry black holes at the cores of otherwise unremarkable galaxies. And what happens after a galaxy goes through an HyLIRG phase? One possibility is that it burns out. It uses up or expels all of its star-forming fuel, then fades into a quiet, red, elliptical galaxy. Another possibility is that it transitions into a quasar, or maybe was already one all along. In fact, many HyLIRGs show spectral signatures of both intense star formation and AGN, active galactic nucleus, activity, suggesting that they might be hybrids, caught in a cosmic identity crisis, doing everything all at once. This overlap with quasars is particularly fascinating. Quasars are known for their incredible luminosity, also powered by supermassive black holes. But while quasars are mostly visible in optical and X-ray wavelengths, HyLIRGs live in the infrared. Could they be two sides of the same coin, different evolutionary stages of the same kind of galaxy? Some researchers think HyLIRGs might be quasars in disguise, their light redirected and reprocessed by thick clouds of dust. Others believe HyLIRGs represent an earlier stage, before the dust has been cleared out. There's even a name for this transitional theory, the quasar evolutionary sequence. It starts with a dusty, starburst-driven HyLIRG. Over time, As the black hole in the center grows and the feedback blows out surrounding material, the galaxy morphs into a visible quasar. Eventually, when the fuel is gone and the light fades, it settles into a quiet, massive galaxy. If this theory is correct, then HyLIRGs aren't just impressive, they're a necessary step in the life cycle of the universe's most powerful objects. But for all our theories, HyLIRGs still leave more questions than answers. Why do some galaxies enter this phase while others never do? What triggers the switch? Is it purely mergers? Or are there hidden environmental factors, dark matter halos, gas accretion rates, black hole spin, that play invisible roles? And how common were HyLIRGs in the early universe compared to now? If they were more frequent back then, what does that tell us about how galaxies formed and evolved over time? Another curiosity is the role of HyLIRGs in shaping the cosmic web itself. These galaxies, with their enormous energy output and high-speed outflows, may act as sculptors of the intergalactic medium. When they blow material out of their host galaxy, that gas doesn't vanish, it enters the space between galaxies, enriching it with metals, heating it, changing its density and composition. Over millions of years, this feedback could affect how other galaxies form nearby, triggering or suppressing their growth. HyLIRGs, in this sense, might be part of a larger feedback network, an invisible system that regulates star formation across the cosmos. Let's also not forget how much we owe to gravitational lensing when studying HyLIRGs. Because these galaxies are often so far away, their light can be bent and magnified by foreground galaxies through a phenomenon called gravitational lensing. This cosmic magnifying glass gives us a clearer, amplified view of HyLIRGs that would otherwise be too faint or too small to study in detail. Many of our best images and most detailed spectra come from these lucky alignments. Without them, much of what we know about HyLIRGs would still be hidden. What's even cooler is how simulations are beginning to catch up to observations. Using massive computing clusters and advanced algorithms, researchers can now create realistic virtual galaxies and watch them evolve. Some of these simulated galaxies go through HyLIRG-like phases, confirming that the conditions required for hyperluminous activity can, in theory, happen under known physics. But they're rare, which matches what we observe. HyLIRGs are not common, even in simulations, and that scarcity makes them all the more valuable for studying extreme galactic behavior. And we haven't even talked yet about the possibility of HyLIRGs housing multiple black holes. In merging galaxies, it's not uncommon for each original galaxy to bring its own central black hole. These black holes can orbit each other, spiral inward, and eventually merge, events that could send out gravitational waves rippling through space-time. HyLIRGs, with their high rates of mergers and dense cores, may be key sites for such events. Detecting gravitational waves from a black hole merger inside an HyLIRG would be a stunning confirmation of these theories. Then there's the speculation, and yes, it is still speculation, about the role of exotic physics in these galaxies. Some theories propose that HyLIRGs might be powered not just by normal matter processes, but by more unusual ones, dark matter interactions, decaying primordial black holes, or even structures from string theory like cosmic strings. These ideas are on the fringe, of course, but HyLIRGs are so extreme that they invite extreme thinking. If you want to test new physics, you go to the places in the universe where normal physics already seems to be breaking down. And maybe that's what makes HyLIRGs so captivating. They're the ultimate what-if machines. What if galaxies could form stars 1,000 times faster than normal? What if black holes could grow faster than we thought? What if there's a phase of galactic life we've completely underestimated? Every new HyLIRG discovered is a piece of that puzzle, and a reminder that the universe still holds many secrets just beyond our reach. They're like messages from the past, these hyperluminous galaxies. They shine so brightly, so distantly, that when we see them, we're actually looking billions of years backward in time. That light has traveled across a huge stretch of the universe just to reach our telescopes. So when we study HyLIRGs, we're not just looking at powerful objects, we're looking at the young universe at its wildest, most chaotic, and most experimental stage. This raises the idea that HyLIRGs could be snapshots of a very specific era, a kind of cosmic adolescence, when galaxies were figuring out who they were going to become. It's like catching a star athlete during the most intense training of their life, or a volcano at the peak of eruption. HyLIRGs don't last forever. They burn hard, fast, and then settle into something calmer. That makes every one of them valuable, because you're seeing something that won't happen again in that exact way. What's also strange is how little we still understand about what's happening inside these galaxies. When we see that much light coming from an HyLIRG, we have to ask, what's doing all the work? Is it really just star formation? Can stars alone explain 10 to the power of 14 solar luminosities? Probably not. That's where black holes come in. Because when matter spirals into a black hole at high speed, it can release an insane amount of energy. That's what we think is happening in active galactic nuclei. And when the black hole is supermassive, like millions or billions of times the mass of our Sun, the amount of energy it releases can light up an entire galaxy. HyLIRGs often show signs of both intense star formation and active black holes. So maybe that's the recipe? A galaxy merger dumps in a massive amount of gas. That gas fuels both a burst of star-making and a central black hole feeding frenzy. The dust from that process absorbs a huge chunk of the radiation and remits it as infrared. That's why these galaxies are so bright in that part of the spectrum. The dust is doing the rerouting. And ironically, that dust also hides a lot of what's going on, which is why we're only now catching up with what's been happening all along. Think about that. The universe could have had tons of HyLIRGs, even nearby ones, and we would have missed them just because we couldn't see an infrared very well until the last few decades. The cosmic story was playing, but we didn't have the right speakers to hear the bass line. And now that we do, the music sounds completely different. In some ways, HyLIRGs force us to rethink the limits of nature. We used to believe galaxies had a kind of speed limit for forming stars, a cap, beyond which feedback processes would shut everything down. But HyLIRGs regularly exceed that limit. Some form stars at rates of thousands of solar masses per year. That's not just high, it's off the charts. For comparison, our own Milky Way makes maybe 1 or 2 new stars per year. HyLIRGs make 1 or 2 every hour. Now, that kind of pace can't last forever. And it doesn't. Most HyLIRGs go through this hyperproductive phase for tens or maybe hundreds of millions of years, which sounds long, but is actually short on a galactic scale. It's like a sugar rush before a crash. The system becomes unstable, it burns through its fuel, it launches massive outflows, and eventually settles down. The star formation slows. The dust clears. The black hole calms down. And just like that, the HyLIRG is gone. But it leaves behind a much larger, more massive galaxy than before, potentially the kind of elliptical galaxy we see dominating the centers of clusters today. And here's where things get extra interesting. Some researchers think HyLIRGs could be the ancestors of the most massive galaxies we know today. Not just any galaxies, but the ones at the top of the food chain. The big, red, dead ellipticals that sit at the center of galaxy clusters. The ones that no longer make stars but have huge black holes and sprawling halos of hot gas. If HyLIRGs were the wild teenage years, those giant ellipticals are the old, retired titans, remembering the glory days. This evolutionary path ties into the bigger question: how did structure form in the universe? How did we go from a smooth early cosmos to the complex web of galaxies, clusters, and filaments we see now? HyLIRGs are a critical piece of that puzzle because they represent one of the fastest, most extreme forms of structure growth we've ever observed. They take gas, compress it, ignite it, and rearrange matter on scales we can barely comprehend. It's also worth noting how rare HyLIRGs are. In a universe with hundreds of billions of galaxies, we've only found a few hundred HyLIRGs. That scarcity makes each one precious. And most of them are extremely far away, meaning they existed when the universe was young, maybe just 1 to 3 billion years old. That tells us HyLIRGs are a product of the early universe's conditions, a time when gas was more abundant, mergers were more common, and black holes were hungrier. But are HyLIRGs really extinct? Or have we just stopped seeing them because the conditions have changed? Could they still be happening now, in hidden corners of the universe, behind veils of dust too thick for our current instruments? Or could they be taking new forms we haven't recognized yet? There's a kind of cosmic archaeology in trying to find the last remaining HyLIRGs in the nearby universe. Each one is a fossil from a different time, and each one might tell us something the others didn't. One of the biggest game changers in the study of HyLIRGs has been the arrival of machine learning. When you're combing through petabytes of telescope data, looking for faint infrared signals that might point to a new HyLIRG, you need more than just human eyes. AI algorithms can scan the sky much faster, and they're already helping astronomers find objects that would have been missed otherwise. And these algorithms don't just find the obvious candidates. They also uncover strange hybrids, borderline cases, and completely new categories that might expand our definition of what an HyLIRG even is. This might seem small, but it's not. Because redefining what counts as hyperluminous means we may be underestimating how common this phase really is. Maybe there's a whole continuum of galaxies transitioning through different levels of luminosity, and HyLIRGs are just the tip of the iceberg, the most extreme slice of a much larger population. The idea is that we've only been seeing the brightest examples, while countless others are lurking just below the threshold. And this leads us to one of the most fascinating implications of HyLIRGs, their role as cosmic signposts. If you find one, it tells you something important is happening in that region of space. It's a clue that galaxies are merging, that black holes are growing, that matter is being transformed. HyLIRGs are not just objects, they are events. They mark moments in cosmic history where the rules get pushed to their limits. These cosmic signposts, these HyLIRGs, help us trace how the universe evolved on the grandest scales. Because the universe isn't static, it's dynamic, constantly changing. And HyLIRGs are some of the clearest indicators of the processes driving that change. When we find them, we're essentially uncovering evidence of cosmic upheaval, growth spurts, and transformation. They're like the universe's equivalent of fireworks, brief but spectacular shows that light up the darkness and reveal hidden details about what's going on underneath. What's wild is how HyLIRGs tie into the story of black holes and galaxy growth in such a deep way. In recent years, scientists have realized that supermassive black holes and their host galaxies don't grow independently. They grow together, feeding off each other's energy and matter in a complex dance. This connection is known as coevolution. HyLIRGs seem to be the arenas where this coevolution happens at its most intense. The black hole is feasting, shooting out energy in jets or winds, while new stars explode to life all around it. This interaction is not peaceful. The energy released by the black hole can blow away the gas and dust that fuels star formation, eventually shutting down the process. It's a kind of cosmic feedback loop, like a thermostat keeping the galaxy from overheating. So, studying HyLIRGs means watching this feedback in action, seeing how the black hole's appetite can regulate the galaxy's growth, and vice versa. The intense infrared light from HyLIRGs also challenges astronomers to develop new ways to see inside. Unlike visible light, infrared can pass through dust clouds. That's why the best tools for studying HyLIRGs include space telescopes equipped for infrared astronomy. The Spitzer Space Telescope and Herschel Observatory opened the doors for us, revealing countless dusty galaxies. But the real game-changer is the James Webb Space Telescope. With its unprecedented infrared sensitivity and resolution, it's starting to peel back the layers of these cosmic beasts in amazing detail. JWST is giving us spectra that show us exactly what kinds of molecules and atoms exist inside HyLIRGs, how the gas moves, and how the black holes are behaving. We can measure the temperature of the dust, the speed of star formation, and the rate at which black holes grow. This is allowing scientists to finally build detailed models of HyLIRGs, not just theories but concrete, testable pictures of what's going on. Another piece of the puzzle is the role of environment. HyLIRGs don't exist in isolation. They tend to be found in crowded, chaotic regions of space, places where galaxies are colliding and merging frequently. These crowded neighborhoods might be essential for creating HyLIRGs because they provide the fuel and disturbances that trigger the extreme activity. That means studying HyLIRGs also tells us about the large-scale structure of the universe, how clusters and superclusters of galaxies form and evolve. There's also an open question about how HyLIRGs fit into the bigger population of luminous galaxies. Before HyLIRGs were discovered, astronomers categorized infrared bright galaxies into luminous infrared galaxies, LIRGs, and ultraluminous infrared galaxies, HyLIRGs. HyLIRGs take this to the extreme. They represent the rarest, most intense outliers in this spectrum. Understanding how HyLIRGs relate to these other classes. Are they simply the upper tail of the same population, or do they represent a fundamentally different process? Remains a hot topic. And the implications for understanding cosmic star formation history are huge. HyLIRGs provide a way to track the peaks and troughs of star formation across billions of years. Since they light up when star formation rates are highest, their numbers and properties give us a kind of cosmic census of star production over time. It helps us answer big questions like, when was the universe at its most fertile? How did galaxy formation slow down? What role did black holes play in that decline? Beyond their scientific importance, HyLIRGs also inspire a kind of cosmic awe. They push us to imagine what it would be like to live in a universe so full of extremes. Galaxies churning out stars at thousands of times the rate of the Milky Way. Black holes consuming matter so voraciously that they outshine entire galaxies. And dust clouds so thick they hide entire star factories from our eyes. It's a universe that's both violent and beautiful, chaotic and structured, familiar and utterly alien. To grasp the scale, think about the energy output. An HyLIRG can emit as much energy in a second as our Sun will emit over its entire 10 billion year lifetime. That's like lighting up a trillion light bulbs all at once. It's almost beyond comprehension, a scale so large that it challenges the way we think about energy, matter, and the forces shaping the cosmos. Scientists are also exploring how HyLIRGs affect their surroundings beyond just their own galaxies. The intense radiation and powerful winds from HyLIRGs can blow out gas into intergalactic space, enriching it with heavy elements forged inside stars. This process of feedback not only shapes the HyLIRG itself but also influences neighboring galaxies and the intergalactic medium. It's a kind of cosmic ecosystem where HyLIRGs act like gardeners, pruning and fertilizing the space around them. The study of HyLIRGs is also connected to the search for the earliest galaxies. Because HyLIRGs are so bright and distant, they provide beacons that help us find and study galaxies from the universe's infancy. Some HyLIRGs date back to when the universe was only a few 100 million years old, a time known as the epoch of reionization. Observing HyLIRGs from this era could unlock secrets about how the first stars and galaxies formed, how the first black holes grew, and how the universe transitioned from darkness to light. Still, many mysteries remain. What exactly triggers the extreme bursts of star formation and black hole growth in HyLIRGs? Are there different types of HyLIRGs with distinct physical processes? How do HyLIRGs evolve into the galaxies we see today? And could there be objects even more extreme that we haven't yet detected? As technology advances, new instruments and surveys will continue to push the boundaries of what we know. Radio telescopes, X-ray observatories, and future space missions will complement infrared data, offering a more complete view of these fascinating galaxies. Combined with powerful computer simulations, these observations will help us build a more detailed and accurate picture of HyLIRGs, their origins, evolution, and ultimate fate. The study of hyperluminous infrared galaxies stands at the crossroads of many of the biggest questions in astrophysics and cosmology. They are windows into the past, keys to understanding galaxy formation, testbeds for theories of black hole growth, and markers of cosmic evolution. Each HyLIRG we discover brings us closer to understanding the wild, vibrant universe we inhabit, a universe where the rules are pushed to their limits and the extraordinary is the norm. The journey to uncover the secrets of hyperluminous infrared galaxies is a testament to how far our technology and understanding of the universe have come, but also a reminder of how much remains unknown. Each discovery opens new questions, forcing astronomers to rethink ideas about star formation, black hole physics, and the cosmic web that connects galaxies across the universe. One fascinating aspect of HyLIRGs is their extreme dust content. These galaxies are shrouded in thick layers of cosmic dust that absorb ultraviolet and visible light from stars and active galactic nuclei, then re-radiate that energy as infrared light. This dust not only hides the galaxy's core processes from traditional telescopes, but also plays a vital role in their evolution. Dust grains serve as the raw material for planet formation, and they also influence the chemistry within galaxies by providing surfaces where molecules can form. The dust's interplay with radiation creates complex feedback loops that regulate star formation and black hole activity. The composition and size distribution of dust in HyLIRGs are areas of active research. Scientists analyze the infrared light spectra to identify specific molecules and elements within the dust clouds. For example, polycyclic aromatic hydrocarbons, PAHs, complex organic molecules, have been detected and serve as tracers of star formation. Observations show variations in dust composition across different HyLIRGs, suggesting diverse evolutionary paths or environmental effects. Another intriguing puzzle is how HyLIRGs fit within the life cycle of galaxies. Are they a brief, extreme phase in the evolution of massive galaxies? Many astronomers believe HyLIRGs represent a transitional stage where two or more gas-rich galaxies collide, triggering massive bursts of star formation and black hole feeding. Over time, this intense activity consumes or expels much of the available gas and dust, eventually leading to the formation of a quiescent elliptical galaxy with a dormant black hole at its center. This scenario fits well with observations showing that many HyLIRGs have disturbed morphologies, tidal tails, irregular shapes, and other signs of recent mergers. However, not all HyLIRGs fit this picture neatly. Some appear to be isolated or less obviously disturbed, suggesting alternative mechanisms might be fueling their luminosity. Possibilities include intense accretion of gas from the cosmic web or secular processes like bar-driven gas inflows within galaxies. Pinning down the dominant mechanisms requires detailed multi-wavelength studies and high-resolution imaging, which are increasingly becoming possible with advances in telescope technology. The relationship between HyLIRGs and active galactic nuclei, AGN, is another critical area. AGN are powered by supermassive black holes actively accreting matter, emitting radiation across the electromagnetic spectrum. In HyLIRGs, the AGN can be deeply buried beneath layers of dust, making them difficult to detect in visible or X-ray wavelengths. However, infrared observations and radio surveys have revealed that many HyLIRGs host powerful AGN, suggesting a close link between the galaxy's infrared brightness and black hole activity. This connection has profound implications for understanding the growth of supermassive black holes in the early universe. HyLIRGs provide direct evidence that black holes can grow rapidly during dusty, gas-rich phases. The energy output from AGN can also regulate star formation by heating or expelling gas, which may explain why star formation eventually shuts down in massive galaxies. Despite these advances, many mysteries remain. The exact timing and sequence of events leading to HyLIRG formation, the detailed physical conditions inside their cores, and the fate of the enormous amounts of gas and dust they contain are still being investigated. Scientists use a combination of observations, theoretical modeling, and simulations to explore these questions, revealing new layers of complexity with each study. The discovery of HyLIRGs also pushes the limits of cosmology and galaxy formation theories. They exist at a time when the universe was a few billion years old, during a peak period of star formation and black hole growth known as cosmic noon. Studying HyLIRGs helps astronomers piece together the timeline of galaxy assembly, revealing how the universe transformed from a simple soup of gas and dark matter into the richly structured cosmos we see today. Furthermore, HyLIRGs challenge us to refine our understanding of the cosmic infrared background, the diffuse glow of infrared light filling the universe, produced mainly by countless dusty galaxies like HyLIRGs over cosmic history. This background light carries information about the aggregate star formation and black hole accretion activity through time, helping astronomers connect individual galaxies to the larger cosmic context. In the grand scale of things, HyLIRGs remind us that the universe is a place of extremes. They are cosmic powerhouses, where the most intense star formation and black hole feeding occur. These galaxies illuminate the dark, dusty corners of the cosmos, revealing the hidden workings of galaxy evolution. Each HyLIRG we observe is a chapter in the universe's ongoing story, a story of creation, transformation, and the incredible forces shaping everything from the tiniest dust grain to the largest cosmic structures. As future observatories come online, from the next generation of space telescopes to massive ground-based arrays, our view of HyLIRGs and their role in the cosmos will become ever clearer. These discoveries promise not only to deepen our understanding of galaxy evolution but also to inspire awe at the sheer power and beauty of the universe. HyLIRGs, shining brightly in the infrared, will continue to guide astronomers through the mysteries of cosmic history, unlocking secrets that have remained hidden for billions of years. The significance of hyperluminous infrared galaxies also extends beyond their immediate environments. These galaxies, with their extraordinary energy output, influence the larger cosmic web, the vast network of filaments and voids formed by dark matter, gas, and galaxies across the universe. Through powerful outflows driven by intense star formation and supermassive black hole activity, HyLIRGs eject gas and enriched material into intergalactic space. This process spreads elements like carbon, oxygen, and iron, the building blocks of planets and life, far beyond the confines of their host galaxies. These outflows can travel hundreds of thousands of light years, enriching the surrounding medium and possibly triggering or suppressing star formation in neighboring galaxies. This cosmic pollination is crucial for understanding how galaxies interact and evolve on large scales. By studying HyLIRGs and their outflows, scientists gain insight into the chemical evolution of the universe and the conditions that lead to the formation of new galaxies and star systems. Another exciting frontier involves the role of HyLIRGs in the reionization of the early universe. After the Big Bang, the universe entered a period called the Dark Ages, when neutral hydrogen filled space and absorbed much of the light. It wasn't until the first stars and galaxies formed that their intense radiation began ionizing this hydrogen, making the universe transparent to light, a phase known as reionization. HyLIRGs, with their intense starbursts and active black holes, may have played a significant role in this process. Although their heavy dust content absorbs much of their ultraviolet radiation, the sheer number and brightness of these galaxies might have contributed enough energy to ionize large regions of space. Understanding this contribution helps astronomers unravel the timeline and mechanisms of the universe's transformation from darkness to light. Detecting HyLIRGs at very high redshifts, meaning very far away and thus seen as they were in the distant past, is challenging but essential. These ancient HyLIRGs provide a window into the early stages of galaxy formation and black hole growth. Observations with powerful telescopes like JWST, ALMA, ATACMS, a large millimeter/submillimeter array, and future facilities will enable astronomers to pinpoint these elusive objects and study their properties in detail. In addition to observational work, theoretical astrophysics plays a crucial role in understanding HyLIRGs. Computer simulations modeling galaxy mergers, star formation, black hole physics, and feedback processes help scientists test hypotheses and interpret complex data. These simulations reveal that HyLIRGs are likely the products of violent interactions, where massive amounts of gas are funneled into galaxy centers, fueling rapid starbursts and black hole feeding. Simulations also predict how HyLIRGs evolve over time, transitioning from chaotic, dusty star factories to more stable, quiescent galaxies. By comparing simulation results with observations, astronomers refine their models and gain deeper insights into the physical processes at play. While the study of HyLIRGs is advancing rapidly, it also challenges existing frameworks in astrophysics. The extreme luminosities and physical conditions found in these galaxies push the boundaries of what we understand about star formation efficiency, black hole accretion rates, and the interplay between dust, gas, and radiation. These extremes act as natural laboratories, allowing scientists to test physical laws under conditions impossible to replicate on Earth. HyLIRGs also spark curiosity about whether even more luminous or extreme galaxies exist. Are HyLIRGs the ultimate peak of galaxy luminosity, or are there rarer objects hiding beyond current detection limits? The search continues, with new surveys scanning the sky at infrared and submillimeter wavelengths, hunting for the brightest, dustiest galaxies in the cosmos. The human fascination with these cosmic giants extends beyond science. HyLIRGs capture the imagination because they embody the universe's power to create dazzling phenomena that are at once destructive and generative. They remind us that the cosmos is a place of constant change and transformation, where creation and destruction go hand in hand. In the vast darkness of space, hyperluminous infrared galaxies shine like hidden beacons, revealing stories of cosmic violence, growth, and rebirth. Their study connects us to the earliest chapters of cosmic history, to the forces shaping galaxies, stars, and black holes, and to the ultimate fate of the universe itself. As we continue to observe and unravel the mysteries of HyLIRGs, we deepen not only our scientific understanding but also our appreciation of the universe's complexity and grandeur. These galaxies, blazing in the infrared, remind us how much there is still to learn, and how every discovery opens new windows into the cosmos, waiting to be explored. HyLIRGs also have a profound influence on the future of galaxy clusters, the massive collections of galaxies bound together by gravity. Galaxy clusters are some of the largest structures in the universe, containing thousands of galaxies, vast amounts of hot gas, and dark matter. When hyperluminous infrared galaxies form within these clusters or their surroundings, their intense energy output can heat the surrounding gas and alter the cluster's evolution. This heating effect, known as feedback, prevents the hot gas in clusters from cooling too quickly and forming new stars at a runaway rate. HyLIRGs, through their starbursts and active galactic nuclei, pump tremendous energy into their environment, helping regulate star formation not just inside themselves, but across the cluster scale. This regulation is critical because without it, galaxy clusters would form far more stars than we observe today. Moreover, the radiation and outflows from HyLIRGs can trigger shock waves that ripple through the intergalactic medium. These shocks compress gas in nearby regions, sometimes sparking bursts of star formation in other galaxies. This means that HyLIRGs don't just influence themselves but can affect the growth and life cycles of multiple galaxies around them, creating a complex network of cosmic interactions. The chemical enrichment from HyLIRGs is equally vital. When massive stars end their lives in spectacular supernova explosions, they release heavy elements into space. These elements mix with the gas expelled by galactic winds from HyLIRGs, enriching the intergalactic medium with the materials necessary for building new stars, planets, and eventually life. Tracking the distribution of these elements helps scientists understand how the raw materials for life spread throughout the cosmos. Another fascinating aspect is the connection between HyLIRGs and cosmic dust production. Dust grains form in the atmospheres of aging stars and in supernova remnants. HyLIRGs, by producing massive numbers of new stars and supernovae, contribute significantly to the dust content of the universe. Understanding the amount and type of dust produced in these galaxies helps researchers piece together the timeline of cosmic dust evolution and how it affects the formation of stars and planetary systems over billions of years. The infrared radiation from HyLIRGs also serves as a critical tool for probing the distant universe. Because dust blocks visible light, many of the most distant and early galaxies are invisible to optical telescopes. Infrared observations, however, can penetrate this dust, allowing astronomers to study the earliest stages of galaxy formation and growth. HyLIRGs thus act as cosmic lighthouses, guiding our understanding of the universe's infancy. Despite all we have learned, many questions about HyLIRGs remain. For example, the exact role of magnetic fields within these galaxies is still unclear. Magnetic fields can influence how gas collapses to form stars and how outflows propagate through the galaxy and beyond. Measuring and modeling these fields in HyLIRGs is a challenging but promising area of research. Additionally, the timescales of the hyperluminous phase are not precisely known. How long do galaxies remain in this extreme state? Is it a rapid, explosive event lasting a few million years, or can it be sustained for much longer? Answering these questions requires long-term observations and statistical studies of many HyLIRGs at different stages. The upcoming generation of telescopes and instruments will revolutionize the study of HyLIRGs. Facilities like the Extremely Large Telescope, ELT, and the Square Kilometre Array, SKA, will provide unprecedented sensitivity and resolution, allowing astronomers to peer deeper into these galaxies' cores and better understand the interplay between stars, black holes, gas, and dust. Space missions equipped with advanced infrared detectors will further enhance our ability to map the distribution of HyLIRGs across cosmic time. These observations will help fill in the gaps in our knowledge about the universe's star formation history, the growth of black holes, and the formation of large-scale cosmic structures. Ultimately, Hyperluminous infrared galaxies represent some of the most energetic and dynamic environments in the universe. They challenge our understanding of how galaxies form, grow, and transform over time. By studying them, we gain insights into fundamental processes that shape not only galaxies but the entire cosmos. These cosmic giants illuminate the dark, hidden parts of the universe, showing us the incredible power of nature on the grandest scales. Their stories are still unfolding, and each new discovery brings us closer to understanding the universe's origins, evolution, and destiny. The fascination with HyLIRGs continues to grow, inspiring scientists and enthusiasts alike to look up at the night sky with wonder and curiosity, knowing that even in the darkest corners of space, there are incredible forces at work, shaping the cosmos in ways we are only beginning to comprehend. The intense activity inside hyperluminous infrared galaxies also opens a window into understanding the life cycles of supermassive black holes. These cosmic giants, millions to billions of times the mass of our Sun, lie at the centers of most large galaxies. In HyLIRGs, they often grow at an extraordinary pace, devouring enormous amounts of gas and dust. As the black hole consumes material, it releases tremendous energy, sometimes outshining the entire galaxy. This energy can take the form of radiation across the electromagnetic spectrum or powerful jets of particles moving close to the speed of light. These jets can pierce through the dense clouds of gas and dust, impacting the galaxy's structure and evolution. Scientists are especially interested in how these feeding black holes, called active galactic nuclei or AGN, interact with the surrounding star-forming regions. Sometimes, the energy released by the AGN can blow away gas and dust, shutting down star formation in a process known as quenching. In other cases, it may compress gas and trigger new bursts of star formation. This push and pull between black hole growth and star formation creates a complex balance inside HyLIRGs. Understanding this balance is crucial because it affects the ultimate shape, size, and future of the galaxy. It also sheds light on how black holes and galaxies have co-evolved over billions of years. Observations show that the relationship between black hole mass and the properties of their host galaxies is surprisingly tight, suggesting that their growth is closely linked. HyLIRGs provide a unique laboratory to study this connection in action during one of the most intense phases of galaxy evolution. Moreover, HyLIRGs challenge some of our basic assumptions about how black holes grow. The massive amounts of dust and gas can obscure the central black hole, making it difficult to detect with traditional telescopes. Advances in X-ray and radio astronomy have helped uncover hidden AGN in HyLIRGs, revealing that many of these galaxies harbor rapidly growing black holes that were previously undetectable. Another mystery revolves around the triggers for these hyperluminous phases. While galaxy mergers are a leading explanation, not all HyLIRGs show clear signs of recent collisions. This raises questions about other possible mechanisms, such as internal instabilities within galaxies or interactions with their environments, that can funnel gas inward. The extreme environments inside HyLIRGs also have consequences for the stars forming there. The intense radiation fields, strong winds, and shocks from supernovae create harsh conditions that can influence how stars form and evolve. Studying these conditions helps astronomers understand how star formation varies across different cosmic environments. In addition, the extreme luminosity of HyLIRGs makes them important probes for cosmology, the study of the universe's large-scale structure and history. By measuring their distances and redshifts, astronomers can map how star formation and black hole activity changed over time, helping to refine models of cosmic evolution. HyLIRGs also offer a glimpse into the future of our own galaxy. While the Milky Way is currently a relatively calm, star-forming galaxy, it will eventually collide with the nearby Andromeda galaxy. Such a merger could trigger a hyperluminous phase similar to those seen in HyLIRGs, dramatically altering our galactic neighborhood. Hyperluminous infrared galaxies stand as monuments to the raw power and beauty of the cosmos. Their study touches on nearly every aspect of modern astrophysics, from star formation and black hole physics to galaxy evolution and cosmology. They challenge us to push the boundaries of technology and theory, inspiring new instruments, missions, and ideas. And they remind us that even in the vastness of space, the universe is filled with dynamic, extreme phenomena that shape everything we see and know. The story of HyLIRGs is still being written, with each discovery opening new questions and mysteries. As we continue to explore these cosmic powerhouses, we deepen our understanding of the universe and our place within it. The energy output of hyperluminous infrared galaxies isn't just a curiosity. It's a key piece of the cosmic puzzle that helps us understand how the universe has changed since the Big Bang. One of the reasons HyLIRGs are so valuable to astronomers is that many of them are seen as they were billions of years ago, when the universe was much younger. This means they offer a direct glimpse into the processes that shaped the early cosmos. In the early universe, galaxies were forming rapidly and often interacting with each other. HyLIRGs, with their intense bursts of star formation and active black holes, reflect the extreme conditions of those times. Studying them helps scientists figure out how common such intense activity was, and how it affected the growth and development of galaxies over cosmic time. The way HyLIRGs shine so brightly in infrared is because they're often filled with thick clouds of cosmic dust. This dust is a double-edged sword. It hides many of the galaxy's features from visible light telescopes, but it also re-radiates absorbed light in the infrared, making these galaxies stand out in this wavelength. This is why infrared astronomy is so important for revealing the hidden universe. Telescopes like the Spitzer Space Telescope and the Herschel Space Observatory have been crucial in uncovering HyLIRGs and studying their properties. Looking ahead, the James Webb Space Telescope, JWST, promises to revolutionize our understanding of these galaxies even further. With its powerful infrared capabilities, JWST will be able to peer through the dust and uncover details about the stars, gas, and black holes inside HyLIRGs with unprecedented clarity. This will allow astronomers to answer long-standing questions about the triggers of HyLIRGs' extreme activity and how they evolve. One particularly exciting avenue of research is the search for the very first HyLIRGs that formed in the universe. Finding these ancient galaxies would provide insights into the conditions that existed shortly after the Big Bang, shedding light on the earliest phases of galaxy formation. It's like looking back in time to see how the first massive structures grew from the primordial soup of particles. Another fascinating area is the role of HyLIRGs in reionization, a key epoch in the early universe when the first stars and galaxies ionized the surrounding hydrogen gas, making the universe transparent to ultraviolet light. Because HyLIRGs are sites of intense star formation and energetic black hole activity, they could have played a significant part in this process. While HyLIRGs are among the most extreme and luminous objects in the universe, they are also rare. Their scarcity makes each one a treasure trove of information. By studying many HyLIRGs across different distances and times, astronomers can piece together a timeline of how galaxies and black holes have influenced each other throughout cosmic history. Even with all the advances, HyLIRGs continue to hold surprises. Their variety in size, shape, and activity level suggests that multiple paths can lead a galaxy into this hyperluminous state. Some HyLIRGs might be dominated by star formation, while others by AGN activity, and some by a mix of both. Untangling these contributions is key to fully understanding these galaxies. In addition to their scientific importance, HyLIRGs inspire us to think about our place in the universe. The tremendous forces at work inside these galaxies remind us that the cosmos is far bigger, more dynamic, and more energetic than anything we experience on Earth. They serve as cosmic laboratories where nature pushes the limits of physics and chemistry. Every time we study an HyLIRG, we're reminded that the universe is still full of mysteries waiting to be uncovered. The more we learn, the more we realize how much remains unknown. But this is the essence of exploration. Each answer leads to new questions, and each discovery opens the door to further wonder. As technology improves and our ability to observe the universe grows, HyLIRGs will remain a central focus of astrophysical research. They are not just distant objects, they are key chapters in the story of everything: the stars, planets, galaxies, and life itself. The quest to understand hyperluminous infrared galaxies connects us to the cosmos in profound ways. It challenges us to look beyond what we see, to peer into the dusty depths of space and time, and to uncover the processes that have shaped the universe we call home. What makes hyperluminous infrared galaxies even more fascinating is how they force us to rethink our understanding of galaxy formation and growth. Traditional models often pictured galaxies as relatively calm places where stars formed slowly over billions of years. But HyLIRGs reveal a much more violent, energetic side of the universe's history, a time when galaxies could flare up dramatically, rapidly building stars and feeding black holes at extraordinary rates. The sheer scale of the energy involved in these galaxies is staggering. Imagine a galaxy shining with the energy output of more than 1 trillion suns, much of it hidden behind curtains of cosmic dust. This hidden power challenges our methods of detecting and measuring galaxies and means we have to use clever techniques to really understand what's going on. Astronomers use observations across the electromagnetic spectrum to piece together the story. Radio waves reveal jets from black holes, infrared traces the warm dust heated by young stars, X-rays reveal high-energy processes near black holes, and visible light can sometimes show the aftermath of galaxy collisions. By combining these different views, scientists get a more complete picture of the galaxy's structure and activity. One puzzle that remains is the exact timeline of these hyperluminous phases. How long do these intense bursts of star formation and black hole feeding last? Some models suggest they might be relatively brief, lasting only tens to hundreds of millions of years, before the galaxy settles down or the energy output pushes gas away, shutting down activity. But measuring this directly is difficult because we see galaxies at different distances and times, like snapshots of a movie. HyLIRGs also provide important clues about the fate of massive galaxies. Many of the largest galaxies in the present-day universe show little star formation and host enormous central black holes. The intense activity seen in HyLIRGs might represent a key stage where galaxies grow quickly, then evolve into these massive, quiescent systems. The interplay between star formation and black hole growth in HyLIRGs also connects to one of astronomy's biggest questions: how did supermassive black holes get so big so fast? Some HyLIRGs host black holes that appear to be growing at their maximum rates, suggesting that the hyperluminous phase is a period of rapid black hole assembly. Understanding this helps us learn about the origin of the most massive black holes seen in the centers of galaxies today. One fascinating aspect of HyLIRGs is the role of cosmic dust. While it obscures visible light, dust grains are essential ingredients in star formation. They help cool the gas clouds, allowing them to collapse and form stars. So, the dust that hides these galaxies' bright hearts also makes their intense starbursts possible. Moreover, the dust composition and distribution can tell astronomers about the history and environment of the galaxy. Some studies find that HyLIRGs contain dust grains similar to those found in our own Milky Way, while others suggest more exotic compositions. This hints at the complex chemical processes happening inside these galaxies during their extreme phases. On a larger scale, HyLIRGs can influence their surroundings beyond their own galaxies. The powerful winds and radiation from HyLIRGs can push material out into intergalactic space, enriching it with heavy elements and shaping the environment around galaxy clusters. This feedback process plays a role in the cosmic ecosystem, affecting future generations of galaxy formation. As our instruments become more sensitive and cover more wavelengths, astronomers are discovering more HyLIRGs, including some that challenge our classification schemes. These discoveries push us to refine our definitions and understand the variety of galaxy behaviors across the universe. Hyperluminous infrared galaxies are more than just cosmic curiosities. They are windows into the most energetic and formative processes in the history of the cosmos. Their study connects multiple fields of astrophysics and opens new frontiers for discovery. The journey to understand HyLIRGs is ongoing. With new telescopes, improved simulations, and innovative techniques, we will continue to unravel their mysteries, learning not only about these spectacular galaxies but about the universe's grand story. The study of hyperluminous infrared galaxies is not just about understanding these galaxies alone. It's about piecing together a much larger cosmic puzzle that spans billions of years and countless interactions. These galaxies sit at a crossroads of cosmic evolution, where the forces of gravity, radiation, and gas dynamics clash on immense scales. Within them, stars are born at breathtaking rates, often hundreds or thousands of times faster than in calmer galaxies like our own Milky Way. These starbursts flood the galaxy with new generations of massive, short-lived stars that burn fiercely, and then explode as supernovae, enriching the galaxy with heavy elements needed for planets and life. Meanwhile, at the heart of many HyLIRGs lies a supermassive black hole voraciously consuming matter and releasing tremendous amounts of energy, sometimes in the form of jets that shoot out at nearly the speed of light. This dual engine of star formation and black hole growth is not just a coincidence. It's a dynamic, interconnected dance that shapes the fate of the galaxy. As these galaxies blaze with energy, the intense radiation and powerful winds generated can blow away or heat up the surrounding gas, effectively putting a halt to further star formation. This feedback mechanism is a crucial piece of the cosmic story because it helps explain why some galaxies stop making stars and become the massive elliptical galaxies we see in the nearby universe today. Without such feedback, galaxies might continue forming stars unchecked, resulting in a universe very different from the one we inhabit. Thus, HyLIRGs represent a phase where galaxies rapidly grow and evolve, but also where internal processes start to regulate that growth, bringing about a kind of cosmic self-control. The timing and effectiveness of this feedback are still active areas of research, with many unknowns that new observations hope to clarify. In addition to the physical processes inside HyLIRGs, their environments also play a critical role. Many hyperluminous infrared galaxies are found in regions of space where galaxy collisions and interactions are common. When two galaxies merge, their gas and dust clouds can compress, triggering massive bursts of star formation. The chaos of a collision can funnel gas toward the center, feeding the supermassive black hole and igniting the active galactic nucleus that often powers the infrared luminosity. These mergers can transform the structure of galaxies, turning spirals into ellipticals, and reshape their future evolution. Understanding how HyLIRGs fit into this cosmic web of galaxy interactions sheds light on how the large-scale structure of the universe influences individual galaxies, and vice versa. Each HyLIRG observed provides a snapshot of this dramatic phase of cosmic evolution, revealing the turbulent life of galaxies in the young universe. The dust itself in HyLIRGs is a fascinating subject. Unlike the tiny dust particles we might think of on Earth, cosmic dust is made of complex molecules and tiny solid particles composed of elements like carbon, silicon, oxygen, and metals. These grains absorb ultraviolet and visible light from stars and black holes, and then re-emit it as infrared radiation. This process not only hides much of the galaxy's activity from optical telescopes, but also makes HyLIRGs some of the brightest objects in the infrared sky. The dust can also grow, evolve, and be destroyed by harsh radiation and shocks within the galaxy, meaning the composition and quantity of dust can tell astronomers about the galaxy's history, the intensity of star formation, and the influence of black holes. The study of dust in HyLIRGs links astrophysics with astrochemistry, revealing how the ingredients for planets and life are forged and distributed in the cosmos. HyLIRGs also challenge astronomers to refine their tools and methods. Because these galaxies are so distant, and their light is heavily absorbed and re-radiated, interpreting the signals they send us is complex. Observing across multiple wavelengths, radio, infrared, X-ray, and more, is necessary to build a complete picture. Instruments like the Atacama Large Millimeter/Submillimeter Array, ALMA, have revolutionized our understanding by allowing astronomers to map cold gas and dust with exquisite detail, uncovering the structures fueling starbursts and black hole activity. Meanwhile, upcoming telescopes such as the James Webb Space Telescope promise to deliver even deeper insights by peering through the dust to study the earliest HyLIRGs, possibly even those formed in the first billion years after the Big Bang. Each technological advance opens new windows onto these enigmatic galaxies, pushing the boundaries of what we know and revealing new mysteries to solve. The implications of HyLIRG research go beyond astrophysics. They touch on fundamental questions about the origin of complexity in the universe. The processes that power HyLIRGs are directly linked to how matter evolves from simple hydrogen and helium atoms into complex structures capable of supporting planets, and ultimately, life. The intense starbursts produce heavy elements like carbon, nitrogen, oxygen, and iron, building blocks for planets and biological molecules. The feedback mechanisms that regulate star formation shape the distribution of these elements throughout galaxies, influencing where and when future generations of stars and planets can form. In this way, Understanding HyLIRGs connects cosmic history to the story of life itself, highlighting the deep interconnections between the largest scales of the universe and the tiniest scales of biology. Despite all we've learned, hyperluminous infrared galaxies remain mysterious in many ways. Their rarity means that each new discovery can surprise astronomers and challenge existing models. Some HyLIRGs appear to be dominated by star formation, others by active black holes, and many by a combination of both. Determining which dominates, and how this balance shifts over time, is key to understanding the life cycle of galaxies. The diversity of HyLIRGs also raises questions about whether there are multiple pathways to becoming hyperluminous. Are these galaxies always the result of mergers? Can isolated galaxies become HyLIRGs under the right conditions? And how do environmental factors like nearby galaxy clusters affect their evolution? These questions drive ongoing research and debate, showing how HyLIRGs sit at the frontier of our cosmic knowledge. In the grand scheme, hyperluminous infrared galaxies are more than just extreme objects. They are crucial signposts in the history of the cosmos. They illuminate how galaxies grow, how stars are born and die, how black holes feed and influence their surroundings, and how the universe transformed from a simple, hot plasma after the Big Bang into the rich tapestry of stars and galaxies we see today. They remind us that the universe is a place of immense power and beauty, where forces far beyond our everyday experience shape the fate of everything around us. Studying HyLIRGs is a journey through time and space, a quest to understand the fiery hearts of galaxies blazing billions of years ago. As technology and knowledge advance, the secrets of these galaxies will continue to unfold, bringing us closer to answering some of the most profound questions about the nature of our universe and our place within it. Each discovery in HyLIRG research is a step forward in our cosmic story, a story that continues to captivate and inspire us all. The immense luminosity of hyperluminous infrared galaxies forces us to confront the limits of what we thought was possible in galaxy formation and energy output. These galaxies emit more energy in the infrared than almost any other known class of objects, rivaling or even surpassing the combined output of entire galaxy clusters in some cases. This level of brightness means that HyLIRGs can be observed across vast cosmic distances, allowing astronomers to probe deep into the universe's past. By studying these galaxies, we effectively look back in time, catching glimpses of the universe as it was billions of years ago, at a time when galaxy formation was at its peak. Each HyLIRG acts like a beacon, revealing conditions in the early universe and providing clues about how the structures we see today came to be. One of the key challenges with HyLIRGs is understanding the balance between the sources powering their incredible luminosity. It's often a complex interplay between intense starburst activity and the energetic phenomena associated with active galactic nuclei, the regions around supermassive black holes where gas is heated to extreme temperatures and jets can be launched at near-light speeds. Differentiating the contributions from star formation and black hole accretion requires detailed spectral analysis and multi-wavelength observations, as these processes emit light in different ways. In some HyLIRGs, star formation dominates, with the light coming mostly from massive, young stars heating surrounding dust. In others, the accretion disk of the central black hole is the primary source, its energy absorbed and re-radiated by dust. This dual nature complicates the picture but also provides a rich field of study to understand how galaxies and black holes grow together. Beyond just their power sources, HyLIRGs challenge our understanding of the environments where galaxies evolve. They are often found in regions of space where galaxy density is high, such as galaxy groups and clusters, environments that promote frequent interactions and mergers. These cosmic collisions can funnel gas toward the galaxy centers, triggering the intense activity seen in HyLIRGs. This suggests that environment plays a crucial role in pushing galaxies into these extreme states. However, the detailed mechanisms of how gas flows are funneled, and how long these intense phases last remain subjects of active research. Observations with telescopes capable of high-resolution imaging and spectroscopy provide insight into the dynamics of gas and stars within HyLIRGs, revealing turbulent motions, shock fronts, and complex structures indicative of violent pasts. The study of HyLIRGs also extends into the realm of cosmic feedback, how galaxies regulate their own growth. The energy output from both starbursts and active nuclei can drive powerful outflows of gas and dust, effectively blowing away the material needed for further star formation. This process can quench the galaxy's growth, halting star formation and black hole feeding and transitioning the galaxy into a quieter phase. Such feedback mechanisms are a cornerstone of modern galaxy evolution models, helping to explain why some galaxies become massive, dead ellipticals with little ongoing star formation. HyLIRGs provide some of the clearest evidence of these feedback effects in action, with observations showing massive winds and outflows that shape both the galaxies themselves and their larger cosmic neighborhoods. The cosmic dust in HyLIRGs plays a crucial role beyond hiding the galaxy's luminous core. Dust grains act as catalysts in star formation by cooling the gas clouds, allowing them to collapse under gravity and form new stars. The composition and amount of dust can inform us about the history of star formation and the processes enriching the galaxy with heavy elements. Dust also affects the radiation transport, scattering and absorbing photons in ways that influence the observed spectra and apparent brightness of these galaxies. Understanding dust physics in HyLIRGs is therefore essential for correctly interpreting observations and constructing accurate models of their evolution. HyLIRGs also help us explore the early universe's chemical evolution. The intense starburst activity rapidly creates heavy elements through nuclear fusion in massive stars, which are then dispersed by supernova explosions. These elements enrich the interstellar medium, contributing to the formation of planets and possibly the ingredients for life. By studying the chemical composition of HyLIRGs at various distances, astronomers can trace how the universe's elemental makeup evolved over time. This connects the distant, exotic universe of HyLIRGs to the more familiar cosmic neighborhood we live in today. The future of HyLIRG research is bright with upcoming technologies. The James Webb Space Telescope, with its unparalleled infrared sensitivity and resolution, promises to revolutionize our understanding by peering deeper into the dusty hearts of these galaxies. Ground-based observatories with adaptive optics and new instruments across the electromagnetic spectrum will complement these efforts, providing detailed views of HyLIRGs' internal structures and environments. As we uncover more about these extraordinary galaxies, we gain not only knowledge about their nature but also critical insights into the processes that shape the universe itself. In many ways, HyLIRGs are cosmic laboratories, offering natural experiments on the limits of star formation, black hole growth, and galaxy evolution. They are places where matter and energy interact on scales that challenge human comprehension, yet studying them brings us closer to understanding the grand narrative of cosmic history. Every new discovery about HyLIRGs helps fill gaps in our knowledge and sparks new questions, fueling the ongoing quest to unravel the universe's deepest mysteries. HyLIRGs don't just stand out because of their incredible brightness. They also challenge the way we classify galaxies and understand their life cycles. Traditionally, galaxies have been divided into a few categories: spirals, ellipticals, irregulars, starburst galaxies, and those with active galactic nuclei. Hyperluminous infrared galaxies blur these boundaries. Their extraordinary energy output and complex internal processes mean they don't fit neatly into one category. Instead, they often represent a transitional phase, caught in a cosmic moment where intense star formation and black hole activity coexist and feed off each other. This transitional nature suggests that HyLIRGs might be snapshots of galaxies in rapid evolution, shifting from gas-rich, star-forming systems to more quiescent, elliptical forms dominated by older stars. Because HyLIRGs are often so distant, sometimes billions of light-years away, we are seeing them as they were when the universe was much younger. This lets astronomers probe how galaxies formed and grew during the universe's peak periods of star formation and black hole activity, roughly 10 billion years ago. In this sense, HyLIRGs are like time machines. By studying their properties and distribution, researchers can build models of galaxy evolution that span cosmic history. These models attempt to explain how the universe transitioned from a hot, dense state filled with simple gas clouds to the richly structured cosmos filled with diverse galaxies, stars, planets, and eventually life. One striking feature of HyLIRGs is how much dust they contain. Dust might seem like a nuisance because it obscures much of the visible light, but it also holds the key to their unique properties. Dust absorbs ultraviolet and visible light from young stars and active galactic nuclei, and then remits that energy in the infrared part of the spectrum. This is why HyLIRGs shine so brightly in infrared. The dust acts like a veil, hiding the violent activity inside, but also transforming the galaxy's energy output into a different form. The amount and temperature of this dust tell astronomers about the conditions inside these galaxies, such as how much star formation is happening and how intense the radiation fields are. Understanding the origins of such massive dust clouds leads us to another fascinating aspect: galaxy mergers. Many HyLIRGs show signs of having collided or merged with other galaxies. These mergers can trigger the intense bursts of star formation and black hole feeding that characterize HyLIRGs. When two galaxies collide, their gas clouds compress and ignite massive starbursts. At the same time, the gravitational disturbances funnel gas toward the central supermassive black holes, fueling the active galactic nuclei. This combined effect can push the luminosity to hyperluminous levels. The dynamics of mergers, how the galaxies swirl around each other, how their stars and gas interact, create chaotic, energetic environments ripe for extreme processes. Looking deeper, we find that HyLIRGs also challenge our understanding of black hole growth. Supermassive black holes in the centers of galaxies grow by feeding on surrounding gas and stars. The energy released during this feeding process can be enormous, sometimes outshining the entire galaxy. In HyLIRGs, this feeding is often shrouded in dust, making direct observation difficult. However, infrared and X-ray observations have revealed clues about the hidden black holes. Understanding how black holes grow during these intense phases is crucial because they impact the evolution of their host galaxies. The energy released can drive winds and jets that blow away gas and dust, regulating star formation and eventually shutting down further growth, a process called feedback. The scale of energy involved in HyLIRGs is almost unimaginable. Some of these galaxies emit as much energy in a single year as the Milky Way does in thousands, or even millions of years. This tremendous power output forces us to rethink the efficiency of star formation and black hole accretion under extreme conditions. How can so much energy be produced and sustained? The interplay of massive star clusters, dense molecular clouds, and active black holes creates a perfect storm of energy generation. Theoretical models and computer simulations help researchers explore these processes, but many questions remain unanswered. For instance, what determines how long the hyperluminous phase lasts? Why do some merging galaxies become HyLIRGs while others don't? These questions push the boundaries of our knowledge and drive new research. HyLIRGs are also interesting from a cosmological perspective because they contribute significantly to the cosmic infrared background, the diffuse glow of infrared light that fills the universe. This background light is thought to be the cumulative emission from all dust-enshrouded star formation and active nuclei throughout cosmic history. HyLIRGs, with their extreme infrared output, represent an important piece of this puzzle. By studying them, astronomers can better understand the total energy budget of the universe, including the hidden star formation that might be missed in visible light surveys. This has implications for understanding how much mass and energy are locked up in stars and black holes over time. Another intriguing area involves the relationship between HyLIRGs and galaxy clusters. Some studies suggest that HyLIRGs are more commonly found in dense environments, where galaxies interact frequently. These environments might promote the mergers and gas inflows that spark hyperluminous activity. Moreover, the energy released by HyLIRGs might influence the surrounding cluster environment, heating the intra-cluster gas and affecting the formation of new galaxies. Thus, HyLIRGs don't just impact themselves but also play a role in shaping larger cosmic structures. The quest to understand HyLIRGs also drives technological advancements. Detecting and studying these galaxies require highly sensitive instruments capable of capturing faint infrared signals from the distant universe. Missions like the Herschel Space Observatory and the Spitzer Space Telescope have provided valuable data, and the recent launch of the James Webb Space Telescope promises to revolutionize the field. With improved infrared sensitivity and spatial resolution, JWST will be able to peer through dust clouds, revealing the detailed inner workings of HyLIRGs and capturing their formation and evolution in unprecedented detail. At its core, the study of hyperluminous infrared galaxies is a journey into the most energetic and transformative events in the universe. These galaxies showcase extremes of star formation and black hole activity, wrapped in thick cocoons of dust, often born from violent collisions of massive galaxies. They provide unique laboratories to test theories about how galaxies grow, evolve, and interact with their environments. Their discovery and ongoing study continually expand our understanding of the cosmos, challenging assumptions and inspiring new questions. HyLIRGs also capture the imagination because they hint at the dynamic and often violent nature of the universe. Far from being quiet, stable islands of stars, galaxies are constantly evolving, shaped by internal and external forces, sometimes producing spectacular bursts of energy that can outshine entire galaxies. These cosmic fireworks reveal the hidden side of galaxy evolution, where gas, dust, stars, and black holes engage in a complex dance that defines the universe's large-scale structure. Hyperluminous infrared galaxies are among the most fascinating and mysterious objects in the cosmos. Their extraordinary brightness, driven by intense star formation and active black holes, wrapped in thick dust clouds, makes them both challenging and rewarding to study. By unlocking their secrets, astronomers gain insight into the processes that built the universe's galaxies and the extreme physics governing energy production on cosmic scales. As new technologies and telescopes push our observational limits, the coming years promise exciting discoveries that will deepen our understanding of these cosmic giants and the universe they inhabit. The study of hyperluminous infrared galaxies, HyLIRGs, brings us face to face with some of the most fundamental questions about the universe. One of the biggest mysteries is how exactly these galaxies accumulate and sustain such enormous amounts of dust and gas that fuel their incredible energy output. While mergers are a popular explanation, not all HyLIRGs show clear signs of recent collisions, so astronomers are investigating other mechanisms that could bring such massive supplies of raw material into these galaxies' centers. For example, some HyLIRGs might form in environments where cold gas streams from intergalactic space continuously feed the galaxy, replenishing its reservoirs and enabling sustained bursts of star formation and black hole activity. This theory ties into broader questions about how matter flows within the cosmic web, the vast network of filaments made of dark matter and gas that connects galaxies across the universe. If such gas accretion is common, it could explain how some HyLIRGs manage to maintain their hyperluminous phase over tens of millions of years, rather than just brief outbursts. Another intriguing question is the role of feedback mechanisms inside HyLIRGs. When supermassive black holes at the centers of galaxies actively feed, they don't just passively consume matter. They also release energy and matter back into their surroundings through powerful jets and winds. These outflows can heat up or blow away the gas that fuels star formation, potentially shutting down the galaxy's growth. Yet, in HyLIRGs, both black hole activity and star formation seem to be operating at maximum capacity simultaneously, defying some of our existing models. Understanding how this balance is achieved, and for how long, is key to piecing together the life cycles of these galaxies. What makes the infrared emission of HyLIRGs so fascinating is that it acts like a cosmic flashlight shining through the dust, revealing processes that would otherwise be invisible. In many ways, dust obscuration acts like a natural filter, hiding the violent environments inside these galaxies from optical telescopes. But it also preserves clues about the composition, temperature, and density of the dust and gas, which helps astronomers reconstruct the timeline and intensity of star formation events and black hole growth. The process of dust formation itself is complex and involves the life cycle of stars. Massive stars end their lives in supernova explosions, spewing heavy elements like carbon, silicon, and iron into space, which then cool and condense into dust grains. Over time, this dust mixes with gas and becomes the raw material for new stars. In HyLIRGs, the cycle appears to be in overdrive. The enormous number of massive stars being formed and dying creates a thick dusty environment that both feeds and masks the galaxy's core activities. To study these galaxies, scientists rely heavily on observations across multiple wavelengths, from radio waves and infrared light to X-rays. Each wavelength band reveals different aspects of the galaxy's structure and activity. For instance, radio waves can trace cold molecular gas, the fuel for star formation, while X-rays can penetrate dust to detect high-energy phenomena near the central black hole. Combining data from these different windows into the galaxy offers a fuller picture of the intense processes underway. HyLIRGs also challenge astronomers to refine their techniques for measuring distances and intrinsic properties of galaxies billions of light-years away. Because of the extreme dust obscuration and complex emission, determining accurate distances, masses, and luminosities is tricky. Scientists use a combination of redshift measurements, which tell how much the universe has expanded since the light left the galaxy, and detailed modeling of the galaxy's energy output across wavelengths. As telescope technology improves, especially with next-generation instruments like the James Webb Space Telescope and upcoming ground-based observatories, astronomers expect to make even more precise measurements and uncover populations of HyLIRGs previously too faint to detect. On a grand scale, HyLIRGs inform our understanding of cosmic evolution. Their abundance and properties at different times in the universe's history serve as markers for when and how quickly galaxies grew, how star formation rates changed, and how supermassive black holes evolved. Surveys show that HyLIRGs were much more common in the early universe, supporting the idea that galaxy mergers and intense star formation were more frequent during cosmic high noon, roughly 8 to 12 billion years ago. This era marked the peak of galaxy building and black hole feeding, and HyLIRGs were among the brightest signposts of that dynamic time. The presence of HyLIRGs also forces us to reconsider the role of dust in galaxy evolution on a larger scale. While dust might seem like a minor component compared to stars and gas, it dramatically influences how we perceive galaxies and interpret their energy output. Dust absorption and re-emission can hide enormous amounts of activity, and can even affect how galaxies cool and contract to form new stars. HyLIRGs highlight the importance of dust in shaping the observational characteristics and physical processes of galaxies. Exploring HyLIRGs opens the door to thinking about the most extreme physical conditions in the universe. Temperatures, pressures, radiation fields, and magnetic forces inside these galaxies reach levels that push the boundaries of known physics. For example, the intense starbursts generate massive clusters of young, hot stars whose winds and supernova explosions shape the interstellar medium in complex ways. Similarly, the feedback from black holes creates shock waves and relativistic jets that can influence the entire galaxy and beyond. Studying these environments allows scientists to test and refine physical theories under conditions impossible to replicate on Earth. Another fascinating aspect is the connection between HyLIRGs and the formation of the most massive elliptical galaxies seen today. It's hypothesized that HyLIRGs represent a crucial phase in the birth of these giant ellipticals. After the intense star formation and black hole feeding in the HyLIRG phase, feedback mechanisms eventually blow away or consume the gas and dust, leaving behind a large population of older stars. This transition phase explains why many massive elliptical galaxies appear red and dead today, devoid of new star formation but full of ancient stars formed during those energetic early stages. HyLIRGs are also important in the context of understanding the cosmic star formation history. The rate of star formation in the universe peaked about 10 billion years ago, and has declined since. HyLIRGs, with their enormous star-forming power, contributed significantly to that peak. Quantifying their role helps astronomers map how galaxies built up their stellar mass over time and how conditions for star formation changed. This, in turn, links to questions about the origin of elements essential for planets and life. HyLIRGs inspire us to think about the future of galaxy evolution and the ultimate fate of such energetic systems. How long can a galaxy sustain such hyperluminous activity before it exhausts its fuel? What will happen after the star formation and black hole feeding stop? Will the galaxy fade quietly or explode violently? These questions tie into broader themes about the life cycle of matter in the universe and the balance between creation and destruction that shapes cosmic history. In every sense, hyperluminous infrared galaxies are cosmic giants of mystery and power. Their study illuminates the universe's most energetic and transformative phases, revealing how galaxies grow, collide, and evolve. As technology advances and observations deepen, we are poised to uncover even more about these dazzling beacons of the cosmos, shedding light on the dark and dusty corners of our universe. As we go even deeper into what hyperluminous infrared galaxies truly represent, we start to see that they're more than just extreme versions of ordinary galaxies. They're almost like cosmic laboratories, giving us rare chances to see what happens when star formation and black hole growth are pushed to their absolute limits. That alone is enough to grab any astronomer's attention. But there's more going on beneath the surface. HyLIRGs aren't just loud, they're complex, layered, and deeply intertwined with the history of the universe itself. Let's talk about the incredible amounts of star formation happening inside these galaxies. In many HyLIRGs, the rate of star birth is so high that it completely outpaces what we see in normal galaxies by factors of hundreds, or even thousands. Some HyLIRGs are forming stars at rates exceeding several thousand solar masses per year. For context, our own Milky Way only creates about 1 or 2 new stars each year. So when astronomers observe these galaxies forming thousands of stars annually, it's not just impressive, it's mind-blowing. But it also raises big questions. Where is all this gas coming from? How does it stay so concentrated in one galaxy without dispersing? And why is it so efficient at turning that gas into stars? The thing is, this isn't just a short-term event. In some HyLIRGs, the starburst phase could last tens of millions of years. That's enough time to form tens of billions of stars, essentially reshaping the galaxy from the inside out. These aren't gentle processes either. Starburst regions are often chaotic and violent, filled with shockwaves from supernova explosions, turbulence from fast stellar winds, and the constant pull of gravity pulling gas clouds into new formations. It's like a city under construction at all hours, with no breaks. One idea that helps explain how these massive star-forming regions come together is that HyLIRGs might have incredibly dense central regions, where gas is packed together so tightly that it's basically impossible not to form stars. Gravity dominates, pulling material inward where it's compressed and heated until new stars ignite. Some researchers think this process is helped along by interactions or mergers with other galaxies, which can funnel even more gas toward the center. The result is a runaway effect. More gas leads to more stars, which creates more heat and pressure, which in turn triggers even more star formation. Then there's the black hole in the middle of it all. In most, if not all, HyLIRGs, the central supermassive black hole is also feeding at an extraordinary rate. When a black hole feeds, it creates what's called an active galactic nucleus, or AGN. These regions can outshine the rest of the galaxy in some wavelengths, blasting out radiation across the electromagnetic spectrum. And when we say these black holes are feeding fast, we mean it. Some of them are growing so rapidly that they challenge our understanding of how black holes form and evolve. In fact, a few HyLIRGs have black holes that are growing close to the theoretical maximum rate, the Eddington limit, which is the point where the radiation from infalling matter starts to push back hard enough to stop new material from falling in. Here's where things get even more interesting. Normally, you'd expect that if a black hole is growing that quickly, the energy it gives off would blow away the surrounding gas and dust, shutting off star formation. That's what happens in many models of galaxy evolution. But in HyLIRGs, we see both processes happening side by side. The black hole is feeding, and the galaxy is still forming stars like crazy. This shouldn't be possible, or at least, it shouldn't last for long. But clearly, something's different in these galaxies that lets both engines run at full throttle without one destroying the other. One theory is that the gas is so thick and widespread that even though some of it gets blown out by the AGN, plenty remains to fuel star formation elsewhere in the galaxy. Or maybe the outflows from the black hole actually compress nearby gas clouds, causing even more star formation in certain areas. It's also possible that we're catching HyLIRGs during a very specific and short-lived moment in their evolution, right before everything gets shut down by powerful feedback. Either way, these galaxies seem to be walking a tightrope, balancing two incredibly powerful and competing processes. We also have to talk about the role of dust, which is everywhere in HyLIRGs. Dust is more than just a nuisance for astronomers. It's a major player in how galaxies evolve. In HyLIRGs, dust doesn't just block visible light, it absorbs it and re-emits it in the infrared. That's why these galaxies are so bright in the infrared in the first place. And by studying that light, scientists can figure out what kind of dust is there, how hot it is, and how it's moving through the galaxy. Some of it is being pushed out by supernova blasts or AGN winds, while other regions might be slowly drifting through the interstellar medium, cooling and mixing with gas until it forms new stars. Because we're seeing HyLIRGs from such great distances, we're also seeing them as they were billions of years ago. Most known HyLIRGs exist at redshifts greater than 1.5, which means the light we see left them when the universe was less than half its current age. In that sense, HyLIRGs are like cosmic time machines. They show us what galaxy formation looked like in the early universe, during a time when things were a lot more chaotic than they are now. It was an age of rapid growth, violent collisions, and the formation of the massive structures we see today. HyLIRGs also raise questions about how common these galaxies were in the past. Were they rare outliers, or were they just the brightest tip of a much larger iceberg? It's likely that there were many more galaxies like HyLIRGs in the early universe, but their light is so faint and their dust so thick that we've only detected the most extreme examples so far. As our telescopes become more sensitive, especially in the infrared and submillimeter ranges, we're likely to find more of these hidden giants. Each new discovery helps piece together a more complete picture of how galaxies grow and evolve over cosmic time. Let's also not forget the connection between HyLIRGs and dark matter. While HyLIRGs themselves are made up of ordinary matter, stars, gas, dust, they live inside massive halos of dark matter. This invisible substance, which doesn't emit or absorb light, exerts a gravitational pull that helps hold galaxies together and guide their formation. The environment provided by these dark matter halos likely plays a big role in the life of HyLIRGs. The more massive the halo, the more gas it can attract, and the more stable it may be against feedback and outflows. Dark matter might also help explain why some HyLIRGs can sustain such high levels of star formation for so long. In a dense dark matter environment, gas can be pulled back into the galaxy after being pushed out by black hole activity or supernovae. This recycling process may help extend the lifespan of the HyLIRG phase, letting it burn brighter and longer than it otherwise would. It's just another example of how deeply interconnected all aspects of cosmic evolution really are. Even with all this, we're still only scratching the surface of what HyLIRGs can teach us. They're rich with secrets, hidden behind curtains of dust and buried under layers of complexity. Every new observation brings fresh questions. Why do some HyLIRGs seem to form stars even more efficiently than others? How do magnetic fields and turbulence influence their evolution? What happens to them after their hyperluminous phase ends? Do they settle into quiet lives as giant elliptical galaxies, or do they go out in dramatic explosions? We don't have all the answers yet, but one thing is clear: HyLIRGs are among the most fascinating and extreme objects in the universe. They represent a key piece of the cosmic puzzle, offering rare insights into the powerful processes that shape galaxies across time and space. And as our tools and techniques continue to evolve, the next few decades of research are almost guaranteed to reveal even more about these incredible galaxies. There's also a strange paradox when it comes to HyLIRGs and their detectability. They're among the brightest objects in the universe in the infrared, yet almost completely invisible in optical wavelengths. You can point an optical telescope right at one and see almost nothing. Just a dark, featureless spot. But switch over to the infrared spectrum, and it suddenly explodes with brightness. This dual nature makes them difficult to study with traditional tools, but incredibly rewarding when you finally tune into the right frequency. It's like walking past what looks like an abandoned building, only to discover there's a rave happening inside when you put your ear to the wall. This also makes them perfect examples of what's often referred to as hidden or obscured star formation. For a long time, astronomers underestimated the total rate of star formation in the early universe because they were only looking at visible light. It was only with the advent of infrared and submillimeter astronomy that they began to realize just how much star formation was hidden behind clouds of dust. HyLIRGs help reveal that a huge portion of cosmic history was happening in secret, invisible to older telescopes, but burning brightly just outside our range of vision. This discovery reshaped our understanding of galaxy evolution. It wasn't just a slow and steady build-up of stars over billions of years. There were brief but intense moments, starbursts, where a galaxy could produce the bulk of its stars in just a few million years. These bursts are short by cosmic standards, but incredibly influential. They set the stage for everything that comes after, including the development of planetary systems and potentially life. HyLIRGs are the smoking guns of these events, proof that the universe often operates in fits of furious activity rather than slow, predictable rhythms. Another striking thing is the diversity of HyLIRGs. Not all of them look or behave the same. Some appear to be the result of massive galaxy mergers, where two or more large galaxies collide and combine into a single, ultraluminous system. Others seem to be more isolated, growing massive through steady accretion of gas from their surroundings. And some are dominated by AGNs, while others are clearly driven more by starbursts. This suggests that HyLIRG isn't a single category so much as a catch-all term for a wide range of extreme galactic phenomena that happen to share one key trait. They shine like a billion suns in the infrared. That diversity also complicates the question of what happens to HyLIRGs when their luminous phase ends. Some might evolve into quiescent elliptical galaxies, those giant, reddish blobs that seem to just sit there, not forming many new stars. Others might continue to evolve more gradually, transforming into spirals or irregular galaxies over time. It depends heavily on the environment, the amount of available gas, the behavior of the central black hole, and even chance interactions with nearby galaxies. This evolutionary ambiguity is part of what makes HyLIRGs so fascinating. They're like a snapshot of a galaxy caught in mid-transformation, with multiple possible futures still open. And yet, despite all this, HyLIRGs still remain surprisingly elusive. They're hard to find, hard to study, and often disappear from view just when things start to get interesting. This is partly due to their distance. Most of them are billions of light years away, meaning we're seeing them as they were in the early universe. But it's also because they're so enshrouded in dust. Even with modern telescopes like the James Webb Space Telescope, JWST, or ALMA, ATACM, a large millimeter/submillimeter array, getting a clear picture of what's going on inside an HyLIRG is a monumental challenge. Yet scientists are making progress. New instruments are allowing astronomers to peel back the layers of dust and look deeper into these galaxies than ever before. Spectroscopy, for example, can be used to analyze the light from HyLIRGs and determine what elements are present, how fast gas is moving, and what kinds of processes are happening inside. This kind of data is essential for building accurate models of galaxy evolution. And HyLIRGs, with their extreme conditions, serve as crucial testing grounds for those models. If a theory about star formation or black hole growth can explain what's happening in an HyLIRG, it probably doesn't hold up. One area of research that's especially promising is gravitational lensing. Sometimes, a closer galaxy or cluster of galaxies will bend and magnify the light from a background HyLIRG, effectively acting like a natural telescope. These lensed HyLIRGs are easier to study because they appear brighter and larger than they actually are. They offer an unparalleled opportunity to zoom in and examine the structure of these distant galaxies in fine detail, something that would otherwise be impossible. In fact, many of the most detailed observations of HyLIRGs have come from gravitational lensing events. Gravitational lensing also reveals how HyLIRGs are distributed throughout the cosmos. By looking at how often lensing occurs, astronomers can estimate how common HyLIRGs are and how they're spread across different regions of space. This kind of statistical information is vital for understanding the large-scale structure of the universe. HyLIRGs, rare though they may be, play a big role in the cosmic web, the vast network of galaxies, filaments, and voids that make up the universe's architecture. The more we study HyLIRGs, the more we realize they're key players in multiple areas of astronomy. They touch on everything from star formation and black hole physics to galaxy evolution and cosmology. They're not just outliers or anomalies. They're central to understanding how the universe grew from a hot, dense fireball into the rich and complex tapestry we see today. Every new HyLIRG discovered is like finding a missing piece in a cosmic jigsaw puzzle, and each one brings us a little closer to seeing the full picture. And the truth is, we've only just begun to understand them. For every HyLIRG we've observed, there could be dozens or hundreds more waiting to be discovered, hidden in the depths of space, cloaked in dust, and shining in wavelengths just beyond what our eyes can see. As our tools get better and our models more sophisticated, the secrets of these galaxies will slowly start to reveal themselves. And when they do, they might just rewrite the way we think about the universe. There's a kind of cosmic irony to HyLIRGs. Their most defining feature, their immense infrared luminosity, is also the very reason they stayed hidden from us for so long. Traditional telescopes, designed to see visible light, just weren't equipped to find them. It took a shift in thinking, a change in how we looked at the universe, to realize we were missing an entire category of galactic activity. And when that shift happened, it opened the floodgates. Suddenly, astronomers were uncovering these incredibly powerful, dust-shrouded galaxies from the early universe that had been there all along, blazing with activity. And they're not just bright, they're ridiculously bright. To give you an idea, our own Milky Way galaxy emits roughly 10 billion times the luminosity of the Sun. That sounds huge, until you compare it to a hyperluminous infrared galaxy, which can emit over 1 trillion times the Sun's luminosity. That's 100 times brighter than the entire Milky Way. And it's not like this is happening in some vast open space with nothing else around. No, this is happening inside a single galaxy. Just imagine the energy output. We're talking about entire regions within these galaxies turning into star factories, pumping out hundreds or even thousands of stars each year. That kind of intensity can't last forever. Star formation on that scale quickly burns through the available gas. But during the time it does last, millions of years, give or take, it can completely transform a galaxy. Massive stars explode as supernovae, spewing elements into space. Radiation from young stars blasts holes in the dust clouds, changing the structure of the galaxy. Meanwhile, the supermassive black hole at the center is feeding like never before, possibly creating powerful jets that tear through the surrounding material. It's a chaotic, violent, transformative process. HyLIRGs are the galactic equivalent of a pressure cooker on the verge of blowing its lid. This is where HyLIRGs become really important for our understanding of black hole and galaxy coevolution. There's a growing belief in astronomy that galaxies and their central black holes grow in tandem, that the growth of one influences the other. HyLIRGs are a perfect place to study that in action. They're producing stars at extreme rates while simultaneously growing their black holes at breakneck speeds. And all of this is wrapped in dense clouds of gas and dust, which both fuels and hides the process. It's as if the galaxy is undergoing a complete renovation, inside and out, behind closed doors. And that's where things start getting weird. Because the more we learn about HyLIRGs, the more it seems like they don't follow the usual rules. Take, for example, the relationship between black hole mass and the mass of a galaxy's bulge, a well-established correlation in astronomy. For most galaxies, this relationship is pretty tight. But HyLIRGs? They seem to mess with that balance. In some cases, the black holes are way more massive than they should be. In others, the galaxy is growing faster than the black hole. It throws off our equations, makes us question our assumptions. It's like trying to weigh a seesaw that keeps changing shape. Even their environments are strange. HyLIRGs often exist in regions of space that are incredibly rich with other galaxies. These protoclusters, essentially the ancestors of modern galaxy clusters, are like nurseries for extreme cosmic events. When galaxies are packed closely together, interactions and collisions become more likely. That means more mergers, more disruptions, and more chances to trigger the kind of intense activity we see in HyLIRGs. These aren't quiet neighborhoods in space. These are war zones. And HyLIRGs are right in the middle of it, lighting up the battlefield like cosmic flares. Now, let's talk about their contribution to the cosmic infrared background. This is the diffuse glow of infrared radiation that fills the universe, and for a long time, scientists weren't sure where it came from. HyLIRGs, as it turns out, are major contributors. Even though they're rare, their extreme brightness makes them significant players. Think of them as the brightest bulbs in a room full of dim ones. Individually, they stand out. Collectively, they help shape the overall glow. Understanding HyLIRGs is key to understanding the cosmic energy budget, the total amount of energy being produced across the universe. But we're still just scratching the surface. The fact is, most HyLIRGs we've detected are from a very specific era of the universe's history, typically around 10 to 12 billion years ago. That was a time when the universe was in its prime star-forming years, what astronomers call the cosmic noon. It's possible that HyLIRGs are tied closely to this era, that they're a kind of natural result of the conditions present at that time. High gas content, lots of mergers, rapidly forming galaxies, it's the perfect recipe. But it also raises the question, why don't we see HyLIRGs in the modern universe? It's a mystery. Either we're just not looking in the right places, or something about the modern universe makes HyLIRGs less likely to form. Maybe there's not enough cold gas left. Maybe the galaxies we have today are too settled, too stable, too boring. Or maybe HyLIRGs are still around, but they've evolved into something else, something we don't recognize. It's like trying to find a firecracker after it's exploded. The pieces are there, but the shape is gone. Another possibility is that HyLIRGs were a kind of cosmic phase that galaxies go through. A brief, dramatic moment in their youth, before settling down into something more ordinary. That would make them even more fascinating, like catching a teenager during their wild years, right before they grow up and become predictable. If that's the case, then HyLIRGs aren't just interesting in their own right. They're time capsules. They show us what galaxies were like before they became the galaxies we know today. But that leads us to another question: what triggers this phase? What makes a galaxy suddenly explode with light and heat and activity? The most likely answer is a combination of factors. A major merger. A huge influx of gas. The right black hole in the right place at the right time. But there's still so much we don't know. And that's what makes HyLIRGs so addictive to study. Every one of them is a mystery, a puzzle waiting to be solved. And as our tools improve, so does our ability to dig deeper. The James Webb Space Telescope, with its unprecedented sensitivity to infrared light, is opening doors we never thought possible. It can peer through the dust, see the stars forming inside, map the movement of gas, and even detect the chemical fingerprints of the elements involved. With JWST, we're finally able to look inside HyLIRGs, not just at their brightness, but at their structure, their composition, their dynamics. It's like going from looking at a shadow to seeing the full object. What we're finding is both exciting and humbling. Because while HyLIRGs may be extreme, they're also fundamental. They tell us that the universe isn't as neat and orderly as we might like to think. It's messy, chaotic, full of surprises. Galaxies aren't built slowly and carefully. They're forged in fire, shaped by collisions and explosions and violent outbursts of energy. And HyLIRGs are the proof. They are the universe caught in the act of creation, the spark in the forge, the scream in the silence. They remind us that underneath all the neat models and tidy equations, space is still wild. HyLIRGs tear through the idea that galaxies grow gently over time. Instead, they show us that growth can be explosive, that transformation can happen suddenly, in violent fits and bursts. They aren't calm spirals slowly spinning through the void. They are galaxies caught mid-eruption, like volcanoes frozen in a moment of fury. And the more we study them, the more it feels like we're reading a diary from the early universe, a brutally honest account of how messy and unpredictable cosmic evolution can really be. One of the most surprising things we've come to realize is how incredibly compact some of these HyLIRGs are. You'd think with all that energy, all that star formation, they'd be massive in size. But many of them are incredibly dense. Entire galaxies compressed into regions far smaller than the Milky Way. It's as if all that energy and mass is concentrated into a cosmic pressure cooker, creating some of the most intense environments known. These aren't spread-out systems with leisurely star birth happening across light years. No, these are tightly packed chaos machines. The centers of HyLIRGs are often like the downtown core of a city caught in a perpetual riot. Every bit of space is being used, and it's all unstable. And yet, for something so dramatic, HyLIRGs are frustratingly difficult to observe. Because they're so dusty, most of their light doesn't reach us in visible wavelengths. What we do detect is mostly re-radiated infrared light, which requires extremely sensitive instruments to see properly. That's why missions like Spitzer, Herschel, and now JWST have been so critical. These observatories are capable of tuning in to those longer wavelengths and revealing what the universe is trying to hide. Without them, HyLIRGs would still be lurking in the shadows, their energy invisible, their stories untold. What's more, the spectra of these galaxies, the chemical fingerprints they leave behind, are often full of unusual features. In many HyLIRGs, astronomers detect intense emission from polycyclic aromatic hydrocarbons, PAHs, which are molecules created by complex organic processes. These molecules form in the dusty envelopes around young stars, and their presence tells us that HyLIRGs are not just forming stars at insane rates, they're also creating the raw chemical ingredients for planets and potentially even life. It's a reminder that these violent systems may also be seeding the universe with the building blocks of biology. And then there's the feedback, arguably the most important part of the HyLIRG story. Feedback is what happens when all that activity, star formation, black hole accretion, supernova explosions, starts pushing back against the galaxy itself. It's a kind of self-regulation. Too much star formation? Supernovae start blasting out gas, halting the process. Black hole growing too fast? It starts emitting winds and radiation that can blow out the surrounding material. HyLIRGs are a feedback showcase. They're one of the clearest examples we have of how galaxies try to balance growth with destruction, expansion with suppression. But here's the thing, we're still not sure which form of feedback dominates. In some HyLIRGs, the black hole seems to be in charge, regulating everything through powerful jets and outflows. In others, it's the star formation that's driving the show, pushing gas out through superwinds created by overlapping supernova explosions. It could be that there's no single answer, that HyLIRGs fall along a spectrum, with different mechanisms taking the lead depending on the specific conditions. Either way, this tug-of-war between creation and destruction is one of the reasons HyLIRGs are so fascinating. They're not just snapshots of galactic birth, they're case studies in galactic self-control. And all of this raises a bigger question. Are HyLIRGs just a phase in the life of all massive galaxies? Or are they something more exceptional? Are we looking at a universal step in galactic evolution, or are HyLIRGs rare outliers, cosmic oddities that only happen under just the right conditions? The answer matters because it affects how we think about our own galaxy, the Milky Way. Did we once go through an HyLIRG phase, hidden in dust, raging with star formation and black hole activity? Or were we always more calm and collected, growing slowly over billions of years? If HyLIRGs are common, it means our quiet galaxy might have a wild past we've yet to uncover. What's truly wild is that we may already have remnants of HyLIRG activity within our local universe. There are galaxies today that seem to bear the scars of past extreme events, shell structures, tidal tails, massive central bulges, and overgrown black holes. These could be the faded ghosts of HyLIRG ancestors, long since cooled off and quieted down. We can't be sure yet, but if we can piece together the history of these quieter galaxies, we might uncover evidence of long-lost hyperluminous phases buried deep in their past. But let's go even further. Imagine a HyLIRG not as a galaxy, but as a kind of galactic experiment. Each one is a test of cosmic limits. How fast can stars form? How much dust can a galaxy contain? How quickly can a black hole grow before it destabilizes everything? These are nature's stress tests, and they push astrophysical theories to the edge. Every HyLIRG discovered is like a new data point in an extreme corner of parameter space, forcing scientists to refine or rethink their models. And that might be one of the most valuable things about them. HyLIRGs aren't just scientifically important because of their light or their rarity. They matter because they break the rules. They remind us that the universe doesn't have to play fair, that it can go off script at any moment. Every time we think we've figured out how galaxies grow, along comes an HyLIRG to throw a wrench in the machinery. It's the kind of cosmic rebellion that keeps astronomy from ever becoming boring. Now, as we continue mapping the early universe, we're finding more and more HyLIRGs. And each one offers a new mystery. Some have strange morphologies, with distorted arms and warping cores. Others show signs of having multiple galactic nuclei, evidence of ongoing or recent mergers. Some have unusually low metallicities for their brightness, suggesting they formed from relatively pristine gas. Each observation is a puzzle piece, and the picture is still very incomplete. But that's the beauty of it. HyLIRGs are not meant to be understood in a day. They're meant to be explored, layer by layer, mystery by mystery. Some HyLIRGs, when studied up close, even suggest the possibility of triple mergers, not just two galaxies crashing together, but three. That's like trying to track the collision of three high-speed trains all smashing into each other at once, each carrying their own payload of stars, gas, and black holes. The complexity of such events is almost impossible to simulate fully, even with the most powerful computers. And yet, that might be exactly what's going on in the heart of these extreme galaxies. Multiple black holes could be circling each other like cosmic sharks, distorting space-time, shaping gas flows, and feeding off the chaos. We might be witnessing the seeds of some of the biggest supermassive black holes the universe has ever seen, formed not from gentle accretion over eons, but from cosmic violence concentrated in a few 100 million years. Then there's the matter of gravitational lensing. Many HyLIRGs we observe are amplified by foreground galaxies, their light bent and magnified by massive clusters between them and us. Without this natural zoom lens, we might not have seen them at all. But this comes with a catch. It means that many of the HyLIRGs we know today are just the ones we're lucky enough to catch through the lens. There could be many more out there, invisible behind dust, too far away, or not magnified enough for us to detect. That implies a dark truth. We may be missing a significant chunk of the universe's most extreme galaxies. Our view is like looking through a keyhole during a firestorm and trying to guess the size of the blaze. What we're seeing might only be the edge of a much bigger inferno. And think about what this means for cosmic timelines. HyLIRGs seem to appear during very specific windows in the universe's history, particularly between redshifts of 1 and 3, which translates to roughly 8 to 11 billion years ago. That's when the universe was a few billion years old, still forming structure, still chaotic. This era, known as cosmic noon, was the peak of galaxy formation. Stars were being born at rates we rarely see today. HyLIRGs are like the overachievers of that time. They formed more stars, grew faster, and emitted more energy than almost anything else around them. It's like they were racing against the cosmic clock, burning through their gas and dust while they still could, knowing that the universe was cooling, spreading out, and becoming more stable. In many ways, HyLIRGs are time capsules from that era. But unlike the calm and steady light from ancient stars, these are time capsules in crisis. They show us the universe not as a calm place slowly settling into structure, but as a raw battlefield where gravity, gas, and radiation fought for dominance. And because of that, HyLIRGs might actually help us unlock one of the biggest questions in astrophysics. How did galaxies go from chaotic, unstable, gas-rich blobs to the massive, ordered systems we see today? If we can figure out what's happening inside HyLIRGs, we might understand the steps galaxies take to evolve into what we now call normal. But it's not just about galaxies. HyLIRGs also teach us about black holes. In fact, some HyLIRGs are quasars in disguise. At their core, a ravenous black hole is growing at breakneck speed, pulling in matter and heating it until it glows like a mini-sun. But unlike the traditional picture of a quasar, bright, blue, and visible across the universe, HyLIRGs bury their quasars under layers of dust. They're like monsters wrapped in cloaks, invisible unless you know where and how to look. And the more of these hidden quasars we find, the more it changes our understanding of how black holes grow. We used to think quasars were rare, but what if most of them are just hidden, their light smothered by the very stuff feeding them? Some scientists now believe that black hole growth might always begin this way, in secret, under heavy blankets of dust and gas, only emerging later once they've consumed enough to clear out their surroundings. HyLIRGs, in that sense, aren't just special cases. They might be the default mode of early black hole evolution. That means our entire timeline of black hole growth could be wrong. We've been studying the visible ones and missing the buried giants. HyLIRGs are now forcing us to rewrite those narratives. And it gets even weirder. Some HyLIRGs emit strange patterns of radio waves, suggesting the presence of jets, powerful streams of charged particles shot out from the regions near black holes. These jets can stretch thousands or even millions of light years, altering the intergalactic medium around the HyLIRG. They heat up the space between galaxies, prevent cooling, and affect the formation of nearby systems. HyLIRGs with active jets are like cosmic flamethrowers, scorching everything around them. And what's strange is that we still don't fully understand how these jets form, or why some black holes produce them while others don't. HyLIRGs might be a clue, a missing piece in that mystery. There's also the question of their end. What happens to HyLIRGs after their brief, intense lives? Do they settle down into regular elliptical galaxies, burn out and red? Do they retain their dust and become giant lenticular systems? Or do they merge again, evolve further, and become the cores of galaxy clusters? We're still trying to track them through time, to find their descendants and match them to structures we see today. If we can do that, we'll finally understand not just how galaxies are born, but how they die, or rather, how they mature. And perhaps the most poetic part of this whole story is that HyLIRGs, for all their fury, don't last long. They live fast and fade quickly. Some might remain hyperluminous for just tens of millions of years, a blink on cosmic scales. Yet in that time, they can produce more stars than a quiet spiral galaxy might make in billions of years. It's like watching a firework go off in the night sky. Brilliant, overwhelming, unforgettable, but over almost as soon as it starts. And maybe that's what makes them so beautiful. They're reminders that the universe doesn't just build slowly. Sometimes, it explodes into being. But if HyLIRGs are like fireworks, what sparks the fuse? That's still a major puzzle. While galaxy collisions are a big piece of the puzzle, they don't tell the whole story. There are galaxies that merge all the time without producing this kind of extreme luminosity. So what makes some collisions go nuclear while others just stir the pot? Some astronomers think it comes down to timing and gas content. If two gas-rich galaxies collide at just the right angle, at the right speed, and during a specific stage of their evolution, it might create the perfect storm. All that gas suddenly loses its angular momentum, spiraling into the core where it collapses and triggers a starburst, not just a few new stars, but hundreds of thousands per year. On top of that, this same process funnels gas directly into the black hole at the center, supercharging it into an active galactic nucleus. The combination of those two, intense star formation and a raging black hole, creates a feedback loop of energy that lights up the galaxy across all wavelengths. Now let's look at another aspect that's easy to miss, the role of dust. Normally, we think of dust as something that obscures or gets in the way. But in HyLIRGs, dust isn't just a nuisance, it's a major player. Without dust, we wouldn't even know these galaxies exist. It's the dust that absorbs all the ultraviolet and visible light from the stars and black hole activity, and then remits it in the infrared, making HyLIRGs visible in that spectrum. Without the dust, these galaxies might not be hyperluminous in the infrared at all. Dust is not just a side effect, it's the very reason HyLIRGs are what they are. And that raises another fascinating question: where does all this dust come from? Dust in the early universe is a bit of a mystery. It takes time for stars to form, live, and die in ways that produce heavy elements and dust grains. So how can galaxies just a billion years after the Big Bang already be filled with enough dust to blanket an entire quasar? That's something that astrophysicists are still wrestling with. Some think the answer lies in extremely massive stars that live fast and die young, spewing out heavy elements and violent supernova explosions. Others think black hole-driven winds might be playing a role, shaping and spreading dust throughout the galaxy. Whatever the cause, HyLIRGs seem to be dust factories on a massive scale, and that dust tells us as much about their evolution as their light does. Zooming out even more, HyLIRGs may be connected to the larger structure of the universe, the cosmic web of galaxies and dark matter that forms the backbone of everything. Some researchers believe HyLIRGs tend to form in dense environments, maybe at the intersections of filaments in the cosmic web where gas flows inward from multiple directions. In these locations, there's more fuel, more gravitational disturbance, and more opportunity for interactions. If this is true, HyLIRGs might not just be random flukes. They might be the natural byproduct of cosmic geography. In the busiest intersections of the universe, the most chaotic galaxies are born. Another big idea gaining traction is the link between HyLIRGs and the first quasars. If the most powerful quasars we see at high redshift began as HyLIRGs, then we might be witnessing the early life stages of some of the most massive black holes known to science. That has huge implications for models of black hole growth. We currently struggle to explain how some black holes grew so big, so fast, in the early universe. But if HyLIRGs represent an early, dusty, hyperactive growth phase, then maybe these behemoths didn't start small at all. Maybe they were born in a furnace of gas, stars, and chaos, growing rapidly under thick blankets of dust before revealing themselves as quasars. That would flip our understanding of black hole evolution on its head. Of course, studying HyLIRGs isn't easy. Because they're so far away and hidden behind dust, we can't just point an optical telescope at them and see what's going on. We need instruments like the James Webb Space Telescope and AOME, the Atacama Large Millimeter/Submillimeter Array, which can see into the infrared and submillimeter ranges. These tools are giving us our first detailed looks inside HyLIRGs. They're helping us map the gas flows, measure star formation rates, and even catch glimpses of the turbulent regions around their black holes. Every image, every spectrum, adds another piece to the puzzle. Some observations have revealed turbulent winds blowing out of HyLIRGs at hundreds or even thousands of kilometers per second. These winds, driven by black hole activity or supernova explosions, can actually shut down star formation by ejecting gas from the galaxy. It's a paradox. The very energy that lights up the galaxy eventually chokes it. These feedback mechanisms are central to galaxy evolution, and HyLIRGs show us that they don't just happen slowly. They can erupt suddenly and violently, changing the course of an entire galaxy in a few million years. And here's something wild. HyLIRGs might not just be extreme, they might be necessary. Some theorists now argue that galaxies like ours wouldn't exist without HyLIRGs. That the giant ellipticals and massive spirals we see in the local universe may have all gone through HyLIRG-like phases. In that view, HyLIRGs aren't weird, they're a rite of passage. They're what happens when galaxies grow up fast, stumble through chaos, and come out the other side as mature, stable systems. They're the adolescence of galaxies, messy, dramatic, and intense, but critical for shaping the adult form. And yet, despite how much we've learned, there are still so many unanswered questions. Are there different types of HyLIRGs? Do some evolve into quasars while others die quietly? What triggers the transition from a dusty starburst to a visible AGN? Why are some HyLIRGs so much more luminous than others? Are there HyLIRGs we've completely missed because they're too faint, too hidden, or too far away? As we push the boundaries of observation with new space telescopes, better simulations, and deeper surveys, we're likely to find even more of these strange, powerful objects. And each new HyLIRG we discover adds another layer to the story of the universe. They're not just distant curiosities. They're key chapters in the cosmic history book, written in heat, light, dust, and time. One of the most compelling aspects of hyperluminous infrared galaxies is how they push the boundaries of our understanding of galaxy formation. We used to think galaxies evolved gradually, slow star formation, slow gas accretion, calm growth over billions of years. But HyLIRGs throw that out the window. These aren't slow burners, they're galactic flashbangs. They explode into existence, burn through their fuel at a frantic pace, and in some cases, may go dormant or collapse just as fast. This fast-tracked life cycle doesn't fit neatly into earlier models of how galaxies are supposed to behave, and that's a good thing. Because every time something doesn't fit the model, it means the universe is trying to tell us something new. Take, for instance, the relationship between HyLIRGs and dark matter halos. In standard galaxy evolution theory, massive galaxies form within massive dark matter halos, gravitational wells that pull in gas, stars, and other matter. But HyLIRGs often appear in halos that aren't necessarily the largest. That hints at something more complex going on. Maybe there's a threshold, a sweet spot, in halo mass, where conditions are just right for HyLIRG formation. Not too big to cool slowly, not too small to lack fuel, but just enough to trigger a violent, dusty ignition. Or perhaps it's not about halo size at all, but about halo environment, its position in the cosmic web, or its interaction with surrounding structures. Another clue lies in the chemical composition of HyLIRGs. When we analyze the spectra of these galaxies, we often find signs of metals, not in the traditional sense, but in astrophysical terms, where anything heavier than hydrogen or helium counts. That's important, because metals are forged in stars. If HyLIRGs are rich in metals, it suggests they've already gone through at least one round of star formation before entering their current state. That flips our assumptions again. Maybe HyLIRGs aren't brand new galaxies exploding into life, but older systems reigniting in a final blaze. This possibility opens the door to a cyclical view of galaxy activity: quiet phases, violent bursts, and back again. But we still don't fully understand how HyLIRGs shut themselves off. At some point, the starburst stops. The black hole quiets down. The infrared light fades. The dust disperses. What causes that? Is it just fuel exhaustion, like burning through all your firewood in a single night? Or is it feedback? Powerful winds from supernovae and active nuclei blowing the raw material right out of the galaxy? Some observations suggest both play a role. As HyLIRGs ramp up, they generate incredible energy. That energy heats the gas, preventing it from collapsing into new stars. It also drives shockwaves through the interstellar medium, dispersing clouds of star-forming material. In essence, HyLIRGs are so intense, they self-destruct. They're like stars that go supernova, but on a galactic scale. What's more, the life and death of HyLIRGs might shape entire clusters of galaxies. When one HyLIRG goes off, it can send shockwaves and outflows into the surrounding space, influencing other galaxies nearby. In this way, HyLIRGs might act as galactic influencers, reshaping the environment around them through sheer force. These interactions could either spark new star formation in neighboring galaxies by compressing gas, or shut it down by heating and scattering that gas. Either way, HyLIRGs are not isolated. They are part of a cosmic ecosystem, and their behavior has ripple effects far beyond their own boundaries. One area of research that's gaining momentum is the study of HyLIRGs in gravitational lensing systems. When a massive object, like a galaxy cluster, sits between us and a distant HyLIRG, its gravity can bend and magnify the light from that HyLIRG, making it easier to study. These cosmic telescopes allow astronomers to peer deeper into the structure of HyLIRGs than would otherwise be possible. Lens HyLIRGs reveal intricate networks of star-forming regions, gas streams, and black hole outflows, all magnified in stunning detail. These natural zoom lenses are helping us peel back the layers of these galaxies in ways that no single telescope could. And then there's the time factor. When we look at HyLIRGs, we're looking back in time. Many of the most luminous ones are billions of light years away, meaning their light started traveling toward us long before Earth even formed. They show us the universe as it was in its early days, chaotic, hot, dense, and full of raw energy. Every HyLIRG is like a fossil record of the universe's wild youth. But instead of being quiet and buried in rock, they're shouting at us across time and space in the language of infrared radiation. And if all of that wasn't strange enough, there's even speculation that HyLIRGs might be linked to the formation of supermassive black holes that eventually become dormant and sit silently at the center of mature galaxies. Right now, the Milky Way has a supermassive black hole at its core, Sagittarius A. It's relatively quiet today. But could it have once been part of a HyLIRG? Did our galaxy go through its own hyperluminous phase, long before humans, Earth, or even the Sun existed? There's no hard evidence yet, but it's a possibility that astrophysicists are beginning to take seriously. After all, if HyLIRGs are a phase in the life cycle of massive galaxies, then the question isn't whether galaxies like ours went through it. The question is when, and what traces are left behind. The idea that HyLIRGs are a stage, rather than a special category, is becoming more accepted. If that's true, then the universe we see today, the calm galaxies, the ordered spirals, the elliptical giants, are all the result of these brief but critical periods of chaos. HyLIRGs would be the adolescent growth spurt of the cosmos, messy, dramatic, and absolutely essential. And just like real adolescence, it's over quickly. But it leaves permanent marks, in the form of black holes, galaxy structure, chemical enrichment, and the shaping of cosmic neighborhoods. This brings us to the question of how rare HyLIRGs really are. They're incredibly hard to find, yes, but are they truly rare, or just hard to see? As technology improves and our telescopes get better at detecting faint, faraway objects in the infrared, we're beginning to realize there may be many more HyLIRGs out there than we once thought. Some are deeply buried in dust, their light stretched by redshift until it's nearly invisible. Others might be hiding in plain sight, their true luminosity disguised by distance and obstruction. Every new sky survey adds more candidates to the list, and it's becoming clear that HyLIRGs might be just the tip of a much larger iceberg. And that idea, that the most powerful, energetic galaxies in the universe might actually be common, is both exciting and humbling. It means we've barely scratched the surface. That there's a whole universe of violent beauty out there, burning in infrared silence, waiting for us to find it. And if we really start to consider the possibility that hyperluminous infrared galaxies aren't rare at all, that they're just hidden behind layers of dust or so far away their light has been stretched into near undetectability, then we have to rethink the entire timeline of galaxy evolution. That means rethinking when galaxies formed, how fast they evolved, and even what kind of conditions were present in the early universe. HyLIRGs might not be outliers. They might actually be the norm, the natural way galaxies behave at their most active stage. That possibility is earth-shaking, because it reframes the calm galaxies we see nearby today not as the main characters, but as the quiet aftermath of something far more dramatic that happened billions of years ago. And when you think about it like that, it changes what the universe looks like in your mind. We often picture the cosmos as this quiet, starry expanse, peaceful, dark, maybe a little cold and lonely. But if HyLIRGs were everywhere, lighting up the sky in infrared, then the early universe wasn't calm at all. It was violent, explosive, blazing with heat and energy. Instead of a silent void filled with the occasional point of light, imagine a sky teeming with infrared firestorms, whole galaxies undergoing wild transformations, giant black holes tearing through clouds of gas, stars forming and dying in chaotic bursts. That's the universe HyLIRGs are revealing to us, one observation at a time. And we still don't know where the energy comes from exactly. We know it's not just stars. The luminosity of these galaxies is so extreme, sometimes over 1 trillion times the brightness of our Sun, that star formation alone can't explain it. That's where the active galactic nuclei, or AGN, come into play. AGNs are powered by supermassive black holes at the center of galaxies. As matter falls into these black holes, it doesn't just vanish, it gets heated to millions of degrees, releasing massive amounts of energy in the process. This energy escapes in jets, winds, and radiation, especially in the infrared, if there's enough dust to absorb and re-emit the light. That interaction between the AGN and the surrounding dust is what makes HyLIRGs so bright. It's like setting a fog bank on fire. The black hole at the center ignites everything around it. The dust, instead of blocking the light, actually makes it more visible in infrared. It soaks up shorter wavelengths and spits them out as long, warm waves that our telescopes can detect. Without the dust, the galaxy wouldn't glow nearly as brightly in infrared. So it's a strange twist. The thing that makes HyLIRGs so hard to see in visible light is also what makes them shine so brightly in infrared. The obstacle becomes the beacon. What makes this even more fascinating is that we can actually track the temperature of the dust itself. HyLIRGs are so powerful that they heat the surrounding dust to temperatures of hundreds of degrees Kelvin, warm by interstellar standards. And by analyzing the shape of the infrared spectrum, astronomers can estimate the dust temperature, which tells us how intense the energy source must be. The warmer the dust, the stronger the power source. So even when we can't directly see the black hole or the starburst, we can measure their fingerprints through the heat they leave behind. Some HyLIRGs also show complex signs of chemical evolution. Using infrared spectroscopy, we can identify specific molecules within the dust and gas. These include polycyclic aromatic hydrocarbons, PAHs for short, which are basically the cosmic version of soot. These PAHs are formed in carbon-rich environments and often indicate that complex chemistry is happening on a massive scale. In some cases, HyLIRGs show unusually strong PAH signatures, suggesting that their dust is being constantly recycled, broken apart by radiation, and reformed in different ways. It's like a chemical factory operating under intense pressure, turning raw elements into more and more complex compounds. And if you go even further, some HyLIRGs might be hiding signs of massive mergers in their molecular gas. When galaxies collide, their gas clouds crash into each other, compressing and heating up. This leads to the formation of massive shock fronts, and we can detect those in the emission lines of carbon monoxide and other molecules. It's another way to catch HyLIRGs in the act of transforming. These aren't just galaxies that are shining brightly. They're galaxies in the middle of violent interactions, tearing themselves apart and reassembling at the same time. It also helps explain the sheer variety we see in HyLIRGs. Some are dominated by starbursts, others by AGN. Some have balanced contributions from both. It's likely that we're seeing them at different stages of a single process. Maybe it starts with a merger, followed by intense star formation. As the central black hole grows, it begins to outshine the stars and takes over as the primary source of energy. Eventually, feedback from the AGN shuts down star formation entirely. And finally, the galaxy settles into a quieter phase, fading from the HyLIRG category but carrying the scars of that intense period forever. And yet, for all the energy, all the data, and all the discovery, there's still this deep mystery. Why are HyLIRGs so rare in the nearby universe? Why don't we see more of them around us today? One answer might be that they've already burned out. Their window of visibility is short, a few 100 million years at most, and by now, most of them have moved on. They've either run out of fuel, or their black holes have gone quiet, or the dust has dispersed. In any case, they're no longer the monsters they once were. What we see today are the ghosts, the remnants of galaxies that once burned like cosmic furnaces. And yet the light from their past is still traveling toward us. That's what makes astronomy so strange and so poetic. We don't observe the universe as it is. We observe it as it was. Every HyLIRG we detect is a message from billions of years ago, a signal that's been flying through space since long before human life even existed. It's a reminder that the universe is vast not just in space, but in time. And that our place in it is temporary, fragile, and incredibly lucky, because we exist in a moment when we can finally begin to understand what happened before us. The idea that HyLIRGs are time capsules from a distant cosmic era makes them more than just interesting astronomical targets. They become keys to unlocking the early history of everything. Each one we detect is a vivid snapshot of an era when galaxies were not calm, structured spirals or lazy ellipticals. They were turbulent engines of chaos. This wasn't the universe of stars gently forming in peace. It was a battleground of matter, energy, radiation, and gravity, all colliding in violent displays of growth. HyLIRGs are proof that even in the deepest darkness of space, the universe is constantly reshaping itself, through fire, collapse, heat, and light. But these galaxies don't just exist in isolation. They are often found in dense regions, surrounded by smaller satellite galaxies and trapped in cosmic filaments that stretch for millions of light years. This web of matter and energy helps feed the HyLIRG's enormous appetite. Cold gas streams in along these filaments, supplying the material needed to sustain such high levels of star formation and black hole growth. This context is crucial. Without the environment, HyLIRGs wouldn't be able to shine the way they do. Their brilliance is not just internal, it's cosmic. It's built into the very architecture of the universe. One of the most jaw-dropping facts about HyLIRGs is just how much matter they can convert into energy. The star formation rates in these galaxies are sometimes over 1,000 times higher than that of the Milky Way. Imagine thousands of suns being born every single year in a single galaxy. The gravitational collapse of dense gas clouds in the galactic core triggers an avalanche of star formation. This results in young, hot, massive stars that live fast and die young, often ending their lives in massive supernova explosions. These explosions further stir the gas and continue the cycle, keeping the galaxy in a state of constant, explosive motion. The interaction between these stars and their environment adds another layer of complexity. Their radiation ionizes nearby gas, creating glowing regions that shine in infrared and even radio waves. These regions, often hidden in visible light due to dust, become beautifully detailed when observed in longer wavelengths. It's like peering through fog with night vision goggles. And as our telescopes become more sensitive, Especially with instruments like the James Webb Space Telescope, we're beginning to see these dusty environments with a clarity that was impossible just a few years ago. There's also evidence suggesting that HyLIRGs can play a major role in shutting down their own activity, a process called quenching. When the central black hole becomes too powerful, the jets and winds it creates can blow away the gas needed to make new stars. This feedback process turns the galaxy from a firestorm into a graveyard, where star formation halts and only older stars remain. That means HyLIRGs don't just build galaxies, they also destroy their own ability to grow. In a way, they're both the architects and the demolition crews of the cosmic landscape. This push and pull, creation and destruction cycle is not only visually stunning but also fundamentally important to how we understand galaxy life cycles. Every massive galaxy we see today may have gone through a hyperluminous phase like this. It may have once burned so brightly that it outshined all its neighbors, before collapsing into the quiet, stable structure we observe now. HyLIRGs aren't exceptions. They're possibly just a stage that most massive galaxies go through. A fiery adolescence before the long maturity. The more we study HyLIRGs, the more questions arise. Why do some become so much more luminous than others? Is it purely a matter of available gas, or are there deeper variables at play, like dark matter halos, magnetic fields, or even exotic physics? What triggers the most extreme examples? Could there be HyLIRGs so bright that we still can't detect them with current instruments? These are the kinds of mysteries that keep astronomers awake at night, not just the answers we have, but the ones we don't even know how to ask yet. And it's not just astronomers who are fascinated. HyLIRGs are drawing attention from physicists, data scientists, even philosophers. Because what they represent is something much bigger than just one kind of galaxy. They're part of a broader question about how complexity emerges from simplicity. The early universe was, in many ways, uniform, a sea of particles, expanding and cooling. Yet, from that simplicity came wild, chaotic beauty, galaxies that erupt like volcanoes, pour out radiation, and shape the very structure of space. There's a kind of poetic symmetry to it all. In the cold, silent void, these galaxies scream. They scream in infrared, in submillimeter waves, in gamma rays. They scream through gravitational interactions, through jets of matter blasting from black holes at nearly the speed of light. They scream across billions of years of time, until the signal reaches us. And what do? We build telescopes. We launch satellites. We tune our instruments to catch that scream and turn it into data. Then we take that data and turn it into understanding. And even though we're using the most advanced tools ever built, from ground-based arrays in Chile to space-based observatories like Herschel and Webb, we're still only scratching the surface. Every HyLIRG we find opens the door to a dozen more mysteries. Some have strange shapes that suggest bizarre merger histories. Others have odd chemical signatures that don't match any known models. A few even seem to show signs of gravitational lensing, their light being bent and magnified by the gravity of foreground objects. That makes them appear brighter and more massive than they actually are. Or maybe they really are that bright, and we just haven't seen the full picture yet. And think about this. We may never be able to observe HyLIRGs directly with our own eyes. The visible light from these galaxies is so absorbed by dust that even the most powerful optical telescopes see nothing but shadows. It's only by stepping outside the limits of human vision, into infrared and submillimeter wavelengths, that these cosmic titans come into view. That tells us something deep about science itself. To understand the universe, we have to go beyond our senses. We have to build machines that can see what we can't, think in ways we don't, and measure things we'll never feel. The more HyLIRGs we find, the more they challenge our assumptions about the universe. We used to think that galaxies slowly built up over time, like a city expanding its suburbs. HyLIRGs say otherwise. They say some galaxies are born in firestorms, massive, quick, and violent. They say the universe wasn't always slow and steady. It had moments of frenzy, of extreme transformation, where the rules bent and the pace accelerated. These galaxies are like those rare individuals in history who rise from nothing and burn out before the world can catch up. And yet, for all their power, HyLIRGs are fleeting. Their hyperluminous phase might last only a few 100 million years, a blink of an eye in cosmic time. They blaze, they transform, they fade. What's left behind might be an elliptical galaxy, a quasar remnant, or something we haven't even identified yet. But during that brief moment, they are among the brightest objects in the universe, and the most mysterious. All of this leads to one final idea, perhaps the most thrilling of all. What if HyLIRGs are the clues we need to understand how the first galaxies ever formed? What if, in their wild brightness, they contain the echoes of the very first structures that emerged from the Big Bang? Maybe by studying HyLIRGs, we're not just looking at distant galaxies. Maybe we're looking at the origins of structure itself. The moment the universe began turning chaos into form. If we take that idea seriously, that hyperluminous infrared galaxies might be relics or analogues of the very first galaxies, then every new discovery of one becomes a kind of archaeological dig, but on a cosmic scale. Think of it like this: instead of unearthing dinosaur bones from under ancient Earth, we're pulling signals from across time, buried under dust and distorted by billions of years of cosmic expansion. Every HyLIRG we detect is like brushing the dust off an ancient fossil, except the dust is literal interstellar matter, and the fossil is a galaxy exploding with more energy than 1,000,000,000,000 suns. But here's something even more mind-bending. Some of the light we see from HyLIRGs started its journey long before our planet even existed. That light passed through the cosmic web, through collisions, warps in space-time, through epochs of cosmic transformation, and only now, after all that time, is it arriving at our tiny little detectors here on Earth or in orbit. When we detect that light, we're not just observing an object, we're witnessing a moment from before the sun was born. Before life on Earth. Before Earth itself. Now think about how rare that is. In the sea of countless galaxies out there, HyLIRGs stand out like supernovae in a dark night. They are not just galaxies, they are events. They are cosmic phenomena that push every model we've built to its limit. And yet, despite their raw intensity, their light is often nearly invisible to our eyes because of the sheer amount of dust. That irony is hard to ignore. The brightest galaxies in the universe, shrouded in darkness. Hidden, not because they're faint, but because they're surrounded by the very materials that make them bright in the first place. That brings us back to the dust. The role of dust in HyLIRGs can't be overstated. Most people think of dust as something mundane, something that just gets in the way. But in space, dust is fundamental. It's made of tiny particles of carbon, silicon, and metals, the building blocks of planets, of atmospheres, of life. In HyLIRGs, this dust absorbs the high-energy light from young stars and re-emits it in the infrared. That's what makes them hyperluminous in that range. Without dust, we wouldn't see HyLIRGs at all. And without HyLIRGs, we might never have known how chaotic, violent, and productive the early universe really was. But dust doesn't just absorb and re-emit light. It also controls the chemistry of the galaxy. It helps cool down gas clouds so they can collapse into stars. It shields delicate molecules from destructive radiation. And in HyLIRGs, the interplay between dust and gas becomes a cosmic balancing act. Too much turbulence, and you get galactic winds blowing everything apart. Too little motion, and the star formation stops. Somehow, HyLIRGs sit right in the middle of this chaos, teetering on the edge of collapse, but still managing to create thousands of stars every year. And in the midst of all this, there's the central black hole, the monster in the core. These black holes aren't just passive masses pulling in matter. They are engines. As they consume gas, they emit energy, not just light, but jets of charged particles that shoot out at near light speed. These jets can stretch for thousands of light years, slicing through the galaxy like knives. They interact with the surrounding matter, shaping it, compressing it, sometimes even triggering more star formation. It's a paradox. The same force that can shut down a galaxy's growth might also be helping it grow in the first place. Some HyLIRGs show evidence of something even stranger: dual black holes. When two galaxies merge, their central black holes eventually spiral toward each other. During that chaotic dance, the galaxy can experience intense waves of star formation and gravitational chaos. Some of the brightest HyLIRGs we know could actually be two galaxies in the process of becoming one. That merging process stirs the gas, compresses the dust, ignites new stars, and feeds the black holes. It's like a galactic wedding, but one with fireworks that could be seen across the observable universe. And it's this merging process that might explain why HyLIRGs are often so bright. Not every galaxy merger creates a hyperluminous infrared galaxy, but the most intense ones, the most gas-rich, dust-choked collisions seem to. That means HyLIRGs aren't just individual galaxies, they're the aftermath of galactic collisions. Collisions that trigger extreme events. Collisions that light up the sky like nothing else. So when we study HyLIRGs, we're also studying galaxy evolution through violence. Through the kind of cosmic events that shape the large-scale structure of the universe. It's also worth asking, what happens after the HyLIRG phase ends? Once the black hole has blown away the dust, once the gas is consumed or scattered, what's left? Some scientists believe HyLIRGs eventually settle into massive elliptical galaxies, the kind we see at the centers of galaxy clusters today. These ellipticals are full of old stars, with little or no new star formation. That would mean the quiet, ancient-looking galaxies we see in our modern universe were once blazing furnaces of infrared light. That's a wild transformation. From chaos to calm. From cosmic storm to stillness. And that raises deeper philosophical questions. Is the universe itself evolving toward calm? Do all things that begin with fire end in silence? Is that the pattern? HyLIRGs force us to think about time in a way that's hard to grasp. They are like fireworks frozen in mid-burst, caught in the act of transformation, with the echo of their energy still rippling across space. When we observe them, we're seeing the middle of the story. Not the beginning. Not the end. Just the part where everything is burning brightest. But it's not just about the big picture. HyLIRGs may even help answer specific questions about our own galaxy. For example, could the Milky Way have gone through a hyperluminous phase in its early history? There's no direct evidence of that yet, but some simulations suggest that even galaxies like ours might have had more active, dusty, star-forming periods. If that's true, then studying HyLIRGs isn't just about looking outward, it's about looking back at ourselves. Back to a time when our galaxy might have been much more violent and chaotic. That connection makes HyLIRGs personal. They're not just distant objects. They're clues to where we came from. Every time we decode one, we get a little closer to understanding not just how galaxies grow, but how matter organizes itself into complexity. Into stars. Into planets. Into the conditions that make life possible. The study of hyperluminous infrared galaxies also forces us to rethink how galaxies influence their surroundings on the largest scales. Because these galaxies are so powerful, their influence isn't limited to themselves alone. The radiation, the winds, and the jets from HyLIRGs can push vast amounts of matter out into intergalactic space, enriching the cosmic environment with metals and dust. This spreading of elements is crucial because it seeds future generations of stars and galaxies, shaping the chemical evolution of the universe. It's like HyLIRGs are cosmic gardeners, scattering seeds far and wide, setting the stage for what comes next. Moreover, the incredible energy output from HyLIRGs contributes to heating the intergalactic medium, the vast, thin gas that exists between galaxies. This heating can prevent gas from cooling and collapsing into new stars in nearby galaxies, effectively regulating star formation on scales far beyond the HyLIRG itself. This feedback mechanism is one of the most important puzzles in modern cosmology, as it helps explain why we don't see too many overly massive galaxies today. HyLIRGs, with their energetic outflows, could be the cosmic throttles controlling the pace of galaxy growth. The challenge of observing HyLIRGs has driven technological advancements in astronomy. Because these galaxies are mostly hidden in infrared wavelengths, traditional optical telescopes can't easily detect them. Instead, astronomers rely on space-based infrared observatories like the Spitzer Space Telescope and Herschel Space Observatory, as well as ground-based submillimeter arrays like ALMA, ATACM, a large millimeter/submillimeter array. These instruments can see through the dust and reveal the intense activity hidden within. Each new observation brings surprises, expanding our knowledge of how these cosmic powerhouses function and how they fit into the universe's history. As these observational techniques improve, scientists are also developing more detailed theoretical models and simulations to understand HyLIRGs better. These simulations incorporate the complex physics of gas dynamics, star formation, black hole feedback, and dust formation. They reveal the delicate balance that HyLIRGs maintain to stay so luminous without tearing themselves apart. It's a dance of gravity and pressure, light and matter, chaos and order, a cosmic symphony written in the language of physics. The existence of HyLIRGs also sparks interesting debates about the limits of galaxy formation. How massive can a galaxy get before it destabilizes? How much gas can a galaxy consume before its black hole feedback halts star formation? HyLIRGs push these limits, acting as natural laboratories to test the boundaries of cosmic evolution. By studying them, we probe the extremes of astrophysics, from how black holes grow to how the first heavy elements formed and spread. Another fascinating aspect of HyLIRGs is their connection to the early universe's reionization epoch. This was a time roughly 13 billion years ago, when the universe's first stars and galaxies ionized the neutral hydrogen fog that filled space. HyLIRGs, with their extreme star formation and energetic processes, might have played a significant role in this cosmic awakening. Their intense radiation could have helped clear the fog, making the universe transparent to ultraviolet light for the first time. Understanding this link helps us piece together the timeline of cosmic history. Interestingly, not all HyLIRGs are the same. There is a surprising diversity among them, depending on factors like their mass, age, environment, and the type of activity dominating their cores. Some are dominated by starbursts, while others are powered mainly by active black holes. This diversity tells us that HyLIRGs are not just a single type of object but a family of galaxies caught in different stages and conditions of their evolution. Each one offers a unique window into different processes shaping galaxies. The study of HyLIRGs also challenges our understanding of cosmic distances and redshifts. Because these galaxies are so bright in the infrared, they can be detected at enormous distances, some of the furthest we have ever seen. This makes them crucial markers for studying the expansion of the universe and the evolution of large-scale structures. Their light, stretched into the infrared by the expansion of space, carries information about the universe's rate of growth and the distribution of matter on cosmic scales. Another layer to consider is the potential connection between HyLIRGs and quasars, the extremely bright centers of galaxies powered by supermassive black holes. Some astronomers suggest that HyLIRGs could represent an early, dust-enshrouded phase of quasar evolution. Over time, as the black hole feeds and grows, it might blow away the surrounding dust, revealing a bright quasar visible in optical wavelengths. This idea implies an evolutionary sequence from HyLIRGs to quasars, which helps explain the variety of active galaxies we see today. The intense star formation in HyLIRGs also means these galaxies produce vast amounts of heavy elements, including carbon, oxygen, and iron, the fundamental building blocks of planets and life. Studying how and where these elements are created and distributed gives insight into the chemical evolution of the cosmos. HyLIRGs act as cosmic forges, where raw materials are synthesized and then spread through galactic winds and outflows. Despite all this progress, many questions remain. What triggers the initial burst of star formation in HyLIRGs? How long does the hyperluminous phase last? Are we missing even more extreme galaxies because they are so deeply obscured? Future telescopes like the James Webb Space Telescope, now operational, and next-generation observatories will push the boundaries of our knowledge. These tools will let us see deeper into the dusty cores of HyLIRGs, revealing the physical processes that power their incredible luminosity in unprecedented detail. We're also beginning to understand that HyLIRGs are not just isolated oddities. They are connected to the cosmic web, the large-scale network of filaments and voids that make up the universe's structure. Their environments can tell us about how matter clusters and flows in the early universe, offering clues to dark matter and dark energy, the mysterious components that dominate the cosmos. HyLIRGs also force us to reconsider the life cycle of galaxies on the grandest scale. From chaotic, dust-enshrouded birth to quiet, elliptical old age, HyLIRGs may mark a critical transitional phase. Their study is rewriting the textbooks on how galaxies grow, evolve, and ultimately fade away. They show us that the universe is not static but a place of constant transformation, where massive explosions of light and energy briefly dominate before giving way to silence and darkness. The fact that HyLIRGs emit primarily in the infrared means they teach us about the hidden universe, the parts we can't see with our eyes alone. There's a lesson here about the limits of perception and technology. Just because something isn't visible to the naked eye doesn't mean it's not there or not important. HyLIRGs remind us that there are still vast realms of the universe waiting to be discovered and understood. As astronomers continue to explore these galaxies, HyLIRGs serve as a powerful reminder of the universe's complexity and beauty. They challenge us to expand our tools, rethink our theories, and push deeper into the unknown. Each new discovery in the realm of hyperluminous infrared galaxies is a step toward a fuller understanding of the cosmos, its origins, its present, and its ultimate fate. Hyperluminous infrared galaxies, HyLIRGs, don't just stand out because of their brightness. They also highlight the intricate dance between gas, dust, and energy in the cosmos. The amount of dust involved in HyLIRGs is staggering. Imagine a galaxy filled with billions of stars wrapped in thick blankets of microscopic particles that absorb almost all visible and ultraviolet light. This dust then heats up and glows brightly in the infrared, turning HyLIRGs into cosmic lanterns visible across billions of light years. The presence of such vast amounts of dust raises many questions. Where does all this dust come from? How does it survive the intense radiation within the galaxy? And what does this dust mean for the galaxy's future? Dust in galaxies generally forms from the remnants of dying stars, specifically from supernova explosions and the winds of aging giant stars. In HyLIRGs, the extreme rate of star formation means that these processes happen on overdrive. Massive stars live short lives, exploding as supernovae and releasing heavy elements and dust into the surrounding space. The dense, dusty clouds that form around these young stars shield them and their neighbors from harsh radiation, allowing new stars to be born in these cozy nurseries. But the story isn't simple. The radiation from the galaxy's central black hole and intense star formation can also destroy dust grains, creating a constant cycle of creation and destruction. This balance affects the galaxy's appearance and evolution. The massive amounts of gas and dust trapped in HyLIRGs also mean that these galaxies are extreme examples of starburst activity. Starbursts are periods when a galaxy forms stars at a rate tens or even hundreds of times higher than a typical galaxy like our Milky Way. In the case of HyLIRGs, star formation rates can reach thousands of solar masses per year. To put that in perspective, the Milky Way forms about 1 or 2 stars each year. This explosive star formation uses up the galaxy's reservoir of gas quickly, which means these galaxies don't stay hyperluminous forever. Eventually, the fuel runs out, and star formation slows down. These starburst phases also have a profound impact on the galaxy's environment. The combined energy from thousands of young, massive stars and supernova explosions drives powerful winds that blow out gas and dust from the galaxy's core. These winds can reach speeds of hundreds or even thousands of kilometers per second, carrying matter far into intergalactic space. This process not only changes the fate of the HyLIRG itself but also enriches the surrounding space with heavy elements, ingredients necessary for forming new stars and planets in other galaxies. In this way, HyLIRGs act as cosmic engines of chemical evolution, spreading the elements forged inside stars throughout the universe. The central black holes in HyLIRGs play a critical role, too. As material spirals into the black hole's accretion disk, it heats up to extreme temperatures and emits enormous amounts of energy across the electromagnetic spectrum. This activity produces what astronomers call active galactic nuclei, AGN. In HyLIRGs, the AGN often coexist with the starburst regions, and it can be challenging to separate their contributions to the total luminosity. Understanding this interplay is crucial because it tells us how black holes and their host galaxies grow together, a process known as coevolution. One of the biggest challenges in studying HyLIRGs is that the thick dust obscures their central regions, making it difficult to observe their cores directly in visible light. This is where infrared and radio observations become invaluable. Infrared telescopes can peer through the dust and reveal the hidden star formation and AGN activity, while radio telescopes can detect jets and outflows produced by the black hole. Combining these observations gives a more complete picture of what's happening inside these complex systems. The extreme conditions within HyLIRGs also make them excellent laboratories for testing the laws of physics under intense pressure and radiation. For example, the interaction between radiation and dust grains can affect the galaxy's structure, influencing how star formation proceeds and how material flows toward the black hole. The balance between gravitational forces pulling matter inward and radiation pressure pushing it outward creates dynamic environments that can change on surprisingly short timescales, sometimes just a few million years, which is brief in cosmic terms. HyLIRGs are often found in the distant universe, which means we're seeing them as they were billions of years ago. This allows astronomers to study how galaxies formed and evolved early in cosmic history. In fact, many HyLIRGs are observed during a period known as cosmic noon, about 10 billion years ago, when star formation and black hole activity in the universe reached their peak. This makes HyLIRGs critical for understanding why the universe looks the way it does today. Observations of HyLIRGs also reveal that they often reside in dense regions of the universe, where galaxies are more likely to interact and merge. These cosmic collisions can trigger the starbursts and black hole feeding that produce HyLIRGs. Studying these environments helps us understand the role of galaxy interactions in driving the universe's evolution. It also sheds light on the fate of galaxy clusters, the largest gravitationally bound structures in the cosmos. The discovery of HyLIRGs has forced astronomers to revise models of galaxy formation and evolution. Older models focus mostly on gradual star formation over billions of years, but HyLIRGs show that rapid, intense bursts of activity are also vital. These bursts can reshape galaxies, alter their star populations, and influence their central black holes. Incorporating HyLIRGs into these models gives us a more realistic picture of how galaxies grow and change over time. Another fascinating area of research is the role HyLIRGs might play in the broader cosmic ecosystem. The material ejected from these galaxies could feed the growth of other galaxies, acting as a kind of cosmic recycling system. This flow of matter between galaxies is a crucial part of the large-scale structure of the universe, influencing how matter clusters and how new galaxies form. HyLIRGs also help us understand the processes that regulate star formation. Too much star formation can quickly deplete a galaxy's gas, while too little star formation can leave it barren. The feedback from starbursts and AGN activity in HyLIRGs seems to keep this balance in check, preventing galaxies from growing too fast or too slow. This regulation is a key piece of the cosmic puzzle, explaining why galaxies come in many different sizes and shapes. The future of HyLIRG research is bright, thanks to advances in telescope technology. Instruments like the James Webb Space Telescope, which operates primarily in the infrared, will provide unprecedented views of these galaxies. Webb's ability to see through dust and its high sensitivity will allow astronomers to study the earliest HyLIRGs, pushing our knowledge back to the universe's infancy. Ground-based facilities like ALMA will continue to map the gas and dust in exquisite detail, revealing the physical processes driving HyLIRGs' extreme luminosity. As we push further, we might discover even more extreme galaxies, perhaps ones that challenge our current definitions of HyLIRGs or reveal new types of energetic activity. These discoveries will help answer fundamental questions about how galaxies and black holes form, grow, and interact. They will also refine our understanding of the universe's evolution from a hot, dense state to the richly structured cosmos we observe today. HyLIRGs remind us that the universe is a place of extremes, where matter and energy collide and combine in spectacular ways. They show that galaxy formation is not always a gentle, gradual process, but can be violent and dramatic. The lessons learned from HyLIRGs extend beyond astronomy, touching on fundamental physics, chemistry, and even the origins of the elements necessary for life. Hyperluminous infrared galaxies are more than just distant curiosities. They are keys to understanding the universe's past and present, windows into the forces shaping galaxies, and markers of the complex relationship between stars, gas, dust, and black holes. Their study pushes the boundaries of human knowledge and technology, inspiring new questions and discoveries. As we look deeper into space and further back in time, HyLIRGs will remain a vital piece of the cosmic puzzle, guiding us toward a fuller understanding of the grand universe we call home. HyLIRGs also challenge astronomers to think about the role of environment in shaping galaxy properties. Unlike more ordinary galaxies that may evolve relatively quietly, HyLIRGs often appear in crowded neighborhoods where gravitational forces from neighboring galaxies cause collisions and mergers. These interactions are not gentle. They can compress gas clouds, triggering rapid star formation, and funneling material into the central black hole. This environment-driven evolution raises questions about how universal galaxy growth processes really are. Are HyLIRGs rare exceptions caused by special circumstances? Or are they a natural phase in the life cycle of many galaxies? Understanding this helps us see the bigger picture of how structures form in the universe. When looking at HyLIRGs through the lens of cosmic time, they serve as snapshots of what might be short-lived, extreme phases in galaxy evolution. The hyperluminous state likely doesn't last forever. As the fuel for star formation and black hole accretion runs low, the galaxy's brightness dims, and it transitions into a more typical galaxy type. But what triggers the end of this phase? Is it simply running out of gas, or does the feedback from the black hole's powerful jets blow out the remaining fuel? Or perhaps a combination of both? These questions remain active research areas, driving the development of new simulations and observations. The dust in HyLIRGs not only obscures the stars and black hole, but also contains important chemical clues. Dust grains carry elements like carbon, oxygen, silicon, and iron, which are essential for forming planets and, ultimately, life. By studying the composition and distribution of dust in HyLIRGs, scientists can learn about the cycle of matter in the early universe. Where did these elements originate, and how were they distributed on a cosmic scale? HyLIRGs provide a laboratory for investigating these fundamental questions, bridging the gap between the formation of stars, galaxies, and the raw materials for life. Because HyLIRGs emit most of their energy in the infrared, their discovery depended heavily on advances in infrared astronomy. Before powerful infrared telescopes were available, these galaxies remained hidden from view. The Infrared Astronomical Satellite, IRAS, launched in the 1980s, was a game-changer, revealing a whole population of bright infrared sources. Since then, missions like the Spitzer Space Telescope and Herschel have built upon this legacy, mapping the infrared universe with increasing detail. The new generation of telescopes continues to push these boundaries, expanding our knowledge of HyLIRGs and the dusty universe. Another aspect of HyLIRGs that fascinates astronomers is their relationship with galaxy morphology, or shape. While the Milky Way is a relatively calm, spiral-shaped galaxy, many HyLIRGs appear to be irregular or disturbed, reflecting the turbulent conditions caused by mergers and starbursts. Some may eventually settle into elliptical galaxies after the dust clears and star formation slows. This transformation from chaotic, hyperactive systems to calmer, mature galaxies is a crucial chapter in understanding the diversity of galaxy forms we see today. The role of magnetic fields in HyLIRGs is another intriguing topic. Magnetic fields influence how gas collapses to form stars and how jets from the black hole are shaped and directed. While magnetic fields are hard to detect directly, radio observations can reveal their presence through polarized emissions. Understanding how magnetic fields interact with the dense gas and dust in HyLIRGs helps explain the dynamics within these extreme galaxies and the mechanisms driving their evolution. HyLIRGs also tie into broader questions about cosmic reionization and the early universe. Some of the most distant HyLIRGs formed when the universe was just a fraction of its current age. These galaxies might have contributed to reionizing the intergalactic medium, turning the universe from opaque to transparent to ultraviolet light. This process was crucial for shaping the universe's structure and allowing galaxies to form more easily. Studying HyLIRGs at great distances helps piece together this complex era. The presence of supermassive black holes in HyLIRGs raises deep questions about how such enormous objects grow so quickly in the early universe. The black holes powering HyLIRGs can be billions of times the mass of the Sun, and they reach these sizes within a relatively short cosmic time. How they manage to accrete enough matter so fast remains one of the big mysteries in astrophysics. HyLIRGs provide a unique opportunity to study this growth process in action, combining clues from both the starburst and AGN components. HyLIRGs also serve as benchmarks for testing galaxy formation models and cosmological simulations. By comparing observations with simulations, scientists can refine their understanding of the physical processes driving star formation, black hole growth, feedback mechanisms, and galaxy mergers. These simulations help explore scenarios that can't be observed directly, such as the detailed internal structure of HyLIRGs, or their future evolution. The intense radiation from HyLIRGs has profound effects on the interstellar medium, influencing the temperature, chemistry, and ionization states of the gas. This affects how stars form and how the galaxy's overall structure evolves. Studying the interplay between radiation and matter in HyLIRGs provides insights into the physical conditions inside galaxies during their most active phases. HyLIRGs also shed light on the cosmic infrared background, the faint glow of infrared light filling the universe. A significant portion of this background comes from dusty galaxies like HyLIRGs, which collectively reveal the history of star formation and galaxy growth across cosmic time. Understanding the sources of this background helps astronomers build a complete picture of the universe's energy budget. Despite the advances in technology, HyLIRGs remain difficult targets for detailed study due to their distance and dust obscuration. Future observatories, including extremely large ground-based telescopes and next-generation space missions, will improve resolution and sensitivity, enabling astronomers to probe the inner workings of HyLIRGs more closely. The study of HyLIRGs also has implications beyond astronomy. The processes observed, extreme star formation, black hole growth, and dust chemistry, reflect fundamental physical and chemical principles. These phenomena connect to fields like plasma physics, chemistry, and fluid dynamics, making HyLIRGs natural laboratories for exploring universal laws under extreme conditions. HyLIRGs represent the dynamic and ever-changing nature of the cosmos. They remind us that the universe is not static but a place of constant birth, destruction, and transformation. Their brilliance in the infrared tells a story of hidden power and complexity, waiting to be uncovered by our instruments and curiosity. As we continue to explore HyLIRGs, each discovery brings new puzzles and insights. These galaxies, once invisible to us, now stand as key pieces in the cosmic puzzle, helping us understand how matter and energy have evolved over billions of years. Their study stretches our imagination and our scientific tools, pushing the boundaries of what we know about the universe. In many ways, HyLIRGs are cosmic giants with secret lives, glowing fiercely in wavelengths we can't see with our own eyes, hiding stories of creation, destruction, and cosmic evolution. They beckon astronomers to look deeper, to unravel their mysteries, and to understand their place in the grand scheme of things. Their intense activity might one day help us understand how our own galaxy, the Milky Way, came to be and what the future holds for it. After all, galaxies like HyLIRGs are thought to be ancestors of the more calmer galaxies we see today. The path forward will be shaped by new observations, refined theories, and collaborations across disciplines. HyLIRGs stand at the crossroads of many areas of astrophysics, from star formation to black hole physics, from dust chemistry to cosmic structure. They embody the complex beauty and mystery of the universe itself. Hyperluminous infrared galaxies, or HyLIRGs, don't just stand out because of their brightness. They also challenge our understanding of how galaxies evolve in the early universe. When we look deep into space and thus back in time, HyLIRGs often appear at distances that mean we're seeing them as they were billions of years ago, during an era when the universe was much younger. This suggests that these cosmic powerhouses were more common in the past than they are now, which raises important questions about how the conditions in the early universe favored their formation. Why were so many of these galaxies undergoing intense starbursts and black hole feeding frenzy back then? What changed that made HyLIRGs rarer today? One big factor is the availability of cold gas, the raw material needed for star formation. Early on, galaxies had more gas around them, left over from the Big Bang and later enriched by the first generations of stars. When galaxies collide or merge, this gas can be compressed, sparking rapid star formation and fueling the central black holes. Over time, as galaxies use up or blow out their gas through winds and radiation, these intense phases quiet down. So, HyLIRGs give us a peek into a high-energy chapter in cosmic history, where galaxies were actively growing and shaping the universe we see today. The environments HyLIRGs live in are often chaotic and crowded. They tend to reside in regions with lots of other galaxies nearby, which increases the chances of collisions and mergers. These events shake things up dramatically, creating turbulent conditions that feed both starbursts and black hole activity. Interestingly, some HyLIRGs appear to be in the middle of merging galaxies, giant clouds of stars and dust tangled in gravitational dance. Observing these merging systems helps scientists understand how such violent interactions can fuel hyperluminous activity. HyLIRGs also reveal a lot about the nature of dust in galaxies. Dust might seem like just tiny particles, but it plays a massive role in shaping what we see. In HyLIRGs, dust absorbs the intense ultraviolet and visible light from stars and black holes, and then remits it as infrared radiation. This makes HyLIRGs invisible in normal light, but incredibly bright in the infrared. The composition, size, and distribution of dust grains affect how the galaxy's light escapes and what wavelengths we detect. Studying this dust helps astronomers understand the life cycle of elements, since dust forms from the remnants of dying stars and eventually contributes to new stars and planets. Understanding the exact mechanisms behind HyLIRG's luminosity also means untangling the contributions of star formation versus the active galactic nucleus, AGN, the supermassive black hole at the center. This is tricky because both processes can produce intense infrared emission. Various techniques, such as spectroscopy, allow astronomers to separate the signals. For example, certain emission lines and features indicate the presence of hot gas heated by black holes, while others reveal star formation rates. This separation is crucial for piecing together the galaxy's story. Is it a starburst galaxy dominated by new stars, or an AGN-dominated galaxy powered by black hole accretion, or some combination of both? HyLIRGs also challenge our models of black hole growth. Black holes in these galaxies are thought to be accreting matter at very high rates, sometimes close to or exceeding the so-called Eddington limit, which is the balance point where radiation pressure pushes against incoming gas. Growing supermassive black holes so rapidly requires unusual conditions, and HyLIRGs offer a rare opportunity to study these extreme environments. How do black holes avoid blowing away their own fuel? How do they manage to gather enough gas to become billions of times the Sun's mass in just a few 100 million years? These are open questions that make HyLIRGs some of the most fascinating objects in astrophysics. Besides their role in black hole growth, HyLIRGs serve as laboratories to study feedback, the process where energy from stars or black holes pushes back on the surrounding gas. This feedback can regulate, or even halt star formation by heating or expelling gas, effectively controlling the galaxy's growth. In HyLIRGs, feedback effects are thought to be intense, given the enormous energy output. Observing how feedback shapes the gas and dust in these galaxies helps scientists understand how galaxies evolve from active star factories to more quiescent systems. Another key mystery involves the timescale of the hyperluminous phase. Is this an extremely brief but violent burst, or does it last for tens or hundreds of millions of years? The answer impacts how we understand the frequency and impact of HyLIRGs on the universe's history. Some evidence suggests that these phases are relatively short-lived but repeat multiple times, possibly triggered by repeated interactions or internal processes. Figuring out these timescales requires combining observations with simulations that model the physics of gas, stars, and black holes. HyLIRGs also tie into the cosmic star formation history. The universe's star formation rate peaked about 10 billion years ago, during the so-called cosmic noon, when many galaxies were forming stars rapidly. HyLIRGs represent the extreme end of this peak, shining light on the upper limits of star formation and energy output. By studying these galaxies, astronomers refine their understanding of how stars formed across cosmic time, and how galaxies like the Milky Way eventually settled into their calmer, mature states. Because HyLIRGs are often so dust-enshrouded, they teach us about how dust evolves in galaxies. Dust grains grow, move, and sometimes get destroyed by radiation and shocks. The balance of these processes affects the infrared emission we see. Understanding this helps astronomers interpret observations not just of HyLIRGs but of all dusty galaxies, giving insights into how dust influences galaxy evolution. The study of HyLIRGs also benefits from new technology like adaptive optics and interferometry. These methods allow telescopes to achieve higher resolution, resolving structures within HyLIRGs despite their vast distances. This means astronomers can start to see the distribution of star formation, the shape of gas flows, and the presence of jets or outflows powered by black holes. Each detail helps refine models and build a clearer picture of these galaxies' complex inner workings. Interestingly, HyLIRGs may also be linked to quasars, the brightest and most energetic AGN we know. Some theories suggest that HyLIRGs represent a phase before a galaxy reveals itself as a quasar. As the dust clears, perhaps blown away by the black hole's powerful winds, the galaxy transitions from being hyperluminous in the infrared to hyperluminous in visible light. This evolutionary path connects different types of active galaxies into a single framework. The chemistry inside HyLIRGs is equally fascinating. The gas clouds contain molecules such as carbon monoxide, water, and more complex organic compounds. By studying the molecular lines in HyLIRGs, astronomers learn about conditions like temperature, density, and the presence of shocks or radiation fields. This molecular fingerprint reveals the processes fueling star formation and black hole growth. HyLIRGs also contribute to the cosmic energy budget. Their extreme luminosities mean they account for a significant fraction of the total energy output in the infrared universe. This helps solve a puzzle about the sources of the cosmic infrared background radiation, the glow from countless distant galaxies. Understanding how much HyLIRGs contribute refines our picture of the universe's energy distribution. On a broader scale, HyLIRGs help us understand galaxy clustering and large-scale structure formation. Because they often appear in dense regions, their distribution traces where matter is concentrated in the universe. Studying HyLIRGs alongside other galaxy populations reveals how matter clumped together under gravity over billions of years. In addition to observational studies, theoretical work on HyLIRGs involves complex computer simulations that model gas dynamics, star formation, black hole physics, and radiation transfer. These simulations test different scenarios for how HyLIRGs form and evolve, helping to interpret observations and predict what future telescopes might see. The study of HyLIRGs is a prime example of how astronomy pushes technology and theory forward. Discovering and characterizing these galaxies required breakthroughs in infrared detectors, space telescopes, and data analysis. Each new generation of instruments opens fresh windows onto HyLIRGs and the dusty universe, revealing more about the extremes of cosmic evolution. HyLIRGs remind us of the universe's incredible diversity and complexity. While galaxies like our Milky Way offer a peaceful, steady picture, HyLIRGs show the wild side, violent bursts of creation, destruction, and energy release. They challenge our understanding and inspire deeper questions about how everything from stars to black holes shapes the cosmos. HyLIRGs continue to captivate astronomers because they represent the most intense episodes of galactic evolution, a period when everything happens fast and with tremendous energy. To understand why these galaxies become hyperluminous, it's essential to consider the interplay between star formation and black hole activity, both of which can feed off the enormous reservoirs of gas and dust that these galaxies harbor. When galaxies collide or interact, tidal forces funnel gas into the core, compressing it and triggering massive bursts of star formation. At the same time, this infalling gas feeds the supermassive black hole at the center, making it grow rapidly and generate enormous radiation that heats the surrounding dust. This intricate dance of feeding and feedback creates a feedback loop that both fuels and limits the growth of stars and black holes. The energy output from the black hole, including powerful winds and radiation, can blow away or heat the surrounding gas, quenching further star formation. But before this happens, the galaxy shines so brightly in the infrared that it outshines even entire clusters of normal galaxies. This fleeting, violent phase is crucial for understanding how galaxies transform from dusty starburst systems into the quieter elliptical galaxies we see in the nearby universe. Another aspect that makes HyLIRGs intriguing is their role in enriching the intergalactic medium. During these intense phases, massive outflows powered by starbursts and black holes eject gas and metals far beyond the galaxy's boundaries. This expulsion of material seeds the surrounding space with heavy elements that will later form new stars and planets in other parts of the cosmos. HyLIRGs, therefore, are not just isolated phenomena but part of the broader cosmic ecosystem, influencing the chemical makeup of the universe over time. The relationship between HyLIRGs and their central black holes raises important questions about the origin of the tight correlation we observe between the mass of black holes and the properties of their host galaxies, such as the stellar bulge mass or velocity dispersion. This relationship suggests a coevolution where black holes and galaxies grow together, regulating each other through feedback processes. HyLIRGs, caught in their most active phase, offer a live snapshot of this coevolution, showing the physical processes that shape this fundamental cosmic connection. The challenge for astronomers studying HyLIRGs lies in their extreme obscuration. Because these galaxies are shrouded in thick blankets of dust, they are virtually invisible in optical light. This has historically made them difficult to detect and study. The development of infrared and submillimeter telescopes, both on the ground and in space, has revolutionized this field. Instruments like the Spitzer Space Telescope, Herschel Space Observatory, and the Atacama Large Millimeter/Submillimeter Array, ALMA, provide the ability to peer through the dust and analyze the galaxy's structure and composition in unprecedented detail. Observations with these instruments have revealed that HyLIRGs come in different flavors. Some are dominated by star formation, producing thousands of new stars per year, much higher than typical galaxies like the Milky Way, which forms only a few stars annually. Others are dominated by an actively feeding black hole, where the energy output is primarily from accretion processes rather than starburst activity. Many HyLIRGs, however, display a mix of both phenomena, making them complex systems to model and understand. One of the surprising discoveries about HyLIRGs is their diversity in size and morphology. Some are compact, with star-forming regions concentrated in the core, while others are extended over tens of thousands of light-years. This structural variety suggests different evolutionary paths and environmental factors at play. Studying these shapes and sizes helps astronomers unravel the timeline and processes behind HyLIRG formation and evolution. HyLIRGs also serve as a testbed for studying the physics of extreme environments. The conditions inside these galaxies push the limits of star formation efficiency, gas density, and black hole accretion rates. Understanding how these systems can sustain such extreme processes without blowing themselves apart helps refine theories of star formation and black hole physics under the most intense conditions. Looking to the future, the James Webb Space Telescope, JWST, promises to transform our understanding of HyLIRGs by providing high-resolution infrared observations. JWST's sensitivity will allow astronomers to peer into the hearts of these galaxies with unprecedented clarity, detecting the signatures of young stars, mapping gas flows, and characterizing the black hole's growth. JWST will also push the search for HyLIRGs to even earlier cosmic times, potentially revealing the first hyperluminous galaxies forming when the universe was only a few 100 million years old. In addition to JWST, planned ground-based observatories like the Extremely Large Telescope, ELT, and the Square Kilometer Array, SKA, will contribute complementary observations. ELT will offer detailed optical and near-infrared views, while SKA will probe the radio emissions associated with star formation and black hole jets. Together, these instruments will create a multi-wavelength portrait of HyLIRGs, unlocking new insights into their nature. HyLIRGs also link to the broader questions about the fate of galaxies. After the hyperluminous phase, feedback from black holes and starbursts can expel or heat the gas, shutting down further star formation and leading to the formation of red and dead elliptical galaxies. These galaxies contain old stars and little gas, marking the end of active growth. HyLIRGs might represent the transition period, providing clues about how the most massive galaxies in the universe assembled their stars and central black holes. The study of HyLIRGs ties into the cosmic web, the large-scale structure of the universe. These galaxies often sit at the intersections of filaments where matter flows converge, providing the gas needed for their intense activity. Understanding how HyLIRGs fit into this cosmic network helps explain how galaxies assemble mass over billions of years and how matter is distributed on the largest scales. Despite the progress made, many puzzles about HyLIRGs remain. For example, the exact triggers of their hyperluminous phases are not fully understood. Are major mergers the primary cause, or can secular processes within isolated galaxies also generate such extremes? The role of environment is also a topic of investigation. Do HyLIRGs preferentially form in dense clusters or more isolated regions? Answering these questions requires large surveys and detailed follow-up observations. Another mystery concerns the ultimate fate of the dust and gas in HyLIRGs. Does most of it get consumed by star formation, blown out by feedback, or locked away in long-lived molecular clouds? The balance of these processes influences how quickly a galaxy evolves and how it appears at different wavelengths. Understanding the life cycle of gas and dust in HyLIRGs informs broader theories of galaxy evolution. Moreover, the connection between HyLIRGs and the growth of supermassive black holes raises fundamental questions about how the earliest and most massive black holes formed in the universe. Did they grow primarily through rapid accretion during hyperluminous phases, or through mergers with other black holes? HyLIRGs provide a window into these extreme growth periods, helping to solve the puzzle of how black holes reached billions of solar masses in just a few 100 million years after the Big Bang. Additionally, HyLIRGs challenge our understanding of star formation laws. The efficiency of star formation in these galaxies seems to be much higher than in typical galaxies, suggesting that under certain conditions, gas can convert into stars with remarkable speed. Investigating these processes could reveal new physics or environmental effects that alter the standard models of star formation. Observations also hint at the presence of complex dynamics within HyLIRGs. Gas and dust can form rotating disks, inflowing streams, and powerful outflows, creating a highly turbulent environment. Mapping these motions helps unravel how gas feeds the black hole while also fueling star formation, and how feedback from the black hole influences the surrounding material. HyLIRGs also inform the study of cosmic reionization, the epoch when the first stars and galaxies ionized the neutral hydrogen filling the early universe. While HyLIRGs typically form later, their intense star formation and black hole activity provide insights into the extreme environments that could have contributed to reionization. Studying HyLIRGs' ancestors helps understand how early galaxies shaped the universe's transparency. Furthermore, HyLIRGs highlight the importance of multi-wavelength astronomy. Because their light is obscured at visible wavelengths, detecting and studying them requires combining infrared, submillimeter, radio, and X-ray data. This holistic approach enables astronomers to piece together the complex physical processes at work. HyLIRGs are more than just bright galaxies. They are natural laboratories for studying the extremes of cosmic evolution. They teach us about the life cycle of galaxies, the growth of black holes, the formation of stars under extreme conditions, and the interconnectedness of cosmic structures. Each HyLIRG observed expands our knowledge and fuels new questions about the universe's most energetic and dynamic phases. Their study exemplifies the synergy between observation, theory, and technology in modern astronomy. As we continue to explore these cosmic beacons, HyLIRGs will remain crucial in unlocking the mysteries of galaxy formation and evolution, helping us understand the forces that shape the universe we live in today. The vast energy output of hyperluminous infrared galaxies, HyLIRGs, is a testament to the incredible power hidden within the universe's most active galactic cores. These galaxies aren't just shining brightly by chance. Their luminosity is a direct reflection of the chaotic and dramatic events unfolding deep within. Gas clouds, compressed by gravitational forces, ignite star formation on a massive scale. At the same time, central black holes devour matter at a frantic pace, producing energy that is absorbed and re-radiated by surrounding dust, making HyLIRGs some of the brightest infrared sources known. One fascinating aspect is the sheer amount of dust in these galaxies. Unlike typical galaxies where starlight can freely escape, HyLIRGs are blanketed in thick layers of dust that absorb the high-energy ultraviolet and visible light emitted by young stars and black hole accretion disks. This absorbed energy heats the dust, causing it to glow intensely in the infrared. This process transforms HyLIRGs into cosmic, infrared beacons that stand out against the backdrop of the universe, yet remain hidden from traditional optical telescopes. This dusty environment also acts as a double-edged sword. While it hides the inner workings of HyLIRGs from view, it also preserves vital clues about their evolution. By studying the infrared light and its characteristics, astronomers can infer the temperature, composition, and distribution of the dust, helping to reconstruct the physical conditions inside. This is akin to using X-rays to see bones inside a body. Infrared observations reveal the hidden skeleton of a galaxy's energetic heart. The timescales over which HyLIRGs remain hyperluminous are relatively short in cosmic terms, often lasting only a few 100 million years. Despite this brief lifespan, these phases can have outsized effects on the galaxy's future. The intense radiation and stellar winds generated during this period can expel large amounts of gas, effectively shutting down star formation by removing the fuel needed to create new stars. This feedback mechanism is critical because it prevents galaxies from growing uncontrollably and helps explain the observed distribution of galaxy sizes and masses in the universe. Interestingly, HyLIRGs often arise from galaxy mergers, where two or more galaxies collide and coalesce. These cosmic collisions funnel enormous amounts of gas into the central regions, igniting both starbursts and black hole-feeding frenzies. The gravitational chaos stirs the gas and dust, leading to complex structures such as tidal tails, shells, and rings observed in some HyLIRGs. These merger remnants provide a snapshot of galaxy assembly in action, revealing how interactions shape the structure and activity of galaxies. However, not all HyLIRGs fit neatly into the merger scenario. Some appear isolated or show signs of secular evolution, slow, internal processes that can also drive gas into the central regions. This diversity hints at multiple pathways to becoming hyperluminous, suggesting that extreme star formation and black hole growth can occur under a range of environmental conditions and histories. The role of supermassive black holes in HyLIRGs is a subject of intense research. These black holes can grow rapidly by swallowing gas and dust, releasing enormous amounts of energy in the process. This energy can manifest as powerful jets or radiation that interacts with the surrounding material. In some cases, the black hole's energy output can outshine the combined light of billions of stars, making the galaxy's nucleus a dominant source of luminosity. The interaction between black hole activity and star formation is complex. On one hand, black hole feedback can suppress star formation by heating or expelling gas. On the other, in some environments, the shock waves and turbulence created by black hole jets can compress gas clouds and trigger new star formation. This delicate balance makes HyLIRGs laboratories for studying the push and pull between growth and regulation in galaxies. Exploring the molecular gas content in HyLIRGs reveals another layer of complexity. Molecular gas, primarily hydrogen molecules, is the raw material for star formation. Observations show that HyLIRGs harbor massive reservoirs of molecular gas, often concentrated in their centers. These dense gas clouds are the sites of intense star-forming activity, where new stars can form at rates hundreds or thousands of times higher than in normal galaxies. Tracing the dynamics of this gas provides insights into the processes fueling starbursts and black holes. For example, high-resolution observations reveal rotating gas disks, inflows feeding the central black hole, and powerful outflows driven by stellar winds or black hole jets. These flows shape the evolution of the galaxy by regulating how much material is available for new stars and black hole growth. Moreover, the chemical composition of HyLIRGs gas and dust offers clues about their history. The presence of heavy elements, or metals, indicates multiple generations of star formation and enrichment. Some HyLIRGs show enhanced abundances of certain molecules, pointing to active chemical processes in their dense environments. Understanding this chemistry helps trace the life cycles of matter in galaxies and the conditions under which stars and planets form. HyLIRGs also provide a window into the early universe. Many are found at great distances, meaning their light has traveled billions of years to reach us. Observing these distant HyLIRGs allows astronomers to study galaxy formation during the universe's formative epochs, shortly after the Big Bang. These early galaxies appear to go through hyperluminous phases more frequently, suggesting that rapid star formation and black hole growth were common in the young cosmos. The distribution of HyLIRGs across cosmic time also informs models of galaxy evolution. The peak in the number of HyLIRGs roughly corresponds to the epoch when the universe was about 2 to 3 billion years old, a period known as cosmic noon, when star formation and black hole activity reached their maximum. Studying how HyLIRGs evolved before, during, and after this peak sheds light on the processes driving galaxy growth and transformation. HyLIRGs are also tied to the formation of massive elliptical galaxies. After exhausting their gas and quenching star formation, HyLIRGs are thought to evolve into elliptical galaxies, large spheroidal systems dominated by old stars. This evolutionary link connects the hyperluminous infrared phase to the broader picture of galaxy morphology and the life cycle of massive galaxies. The discovery of HyLIRGs has also driven technological advancements in astronomy. Detecting these distant and obscured galaxies requires sensitive instruments capable of observing faint infrared signals. The development of space-based infrared observatories has been crucial, allowing astronomers to bypass atmospheric interference that hampers ground-based observations. These advances have opened new windows on the universe, revealing phenomena that were invisible just decades ago. As our observational capabilities improve, the catalog of known HyLIRGs grows. Large surveys using space and ground-based telescopes continue to discover new examples, pushing the boundaries of redshift and luminosity. These growing samples enable statistical studies, helping astronomers identify trends and patterns that clarify HyLIRG formation and evolution. In addition to observational work, theoretical models and simulations play a key role. Computer simulations of galaxy mergers, star formation, and black hole growth help interpret observations and test hypotheses. These models incorporate complex physics, including hydrodynamics, radiative transfer, and feedback processes, striving to reproduce the observed properties of HyLIRGs. Continued refinement of these simulations is essential for deepening our understanding. One of the exciting frontiers is the connection between HyLIRGs and gravitational waves. Merging supermassive black holes and HyLIRGs may produce gravitational waves, ripples in spacetime detectable by future observatories. Studying HyLIRGs could thus contribute to multi-messenger astronomy, linking electromagnetic observations with gravitational wave signals to provide a fuller picture of cosmic events. HyLIRGs also raise philosophical questions about the universe's extremes. They remind us that cosmic structures can reach unimaginable scales of energy and complexity, far beyond anything experienced on Earth. Understanding these galaxies challenges our ideas about the limits of nature and inspires curiosity about the forces shaping the cosmos. Despite decades of study, HyLIRGs continue to surprise. New discoveries reveal unexpected features, from unusual morphologies to surprising chemical compositions. Each new finding prompts fresh questions, driving the ongoing quest to decode these cosmic powerhouses. The study of HyLIRGs is a testament to human curiosity and ingenuity. By unraveling the secrets of these distant, dust-shrouded galaxies, we gain insights not only into their nature but also into the broader workings of the universe. Their story is one of extremes, extreme energy, extreme conditions, and extreme transformation. As we look ahead, HyLIRGs will remain a focal point of astronomical research. With new telescopes coming online and theoretical models advancing, the next decades promise to deepen our knowledge and perhaps reveal even more astonishing aspects of these galaxies. They are a bridge to understanding how the universe built its largest structures, formed its most massive black holes, and forged the heavy elements essential for life. HyLIRGs remind us that the universe is an active, evolving place, full of mysteries waiting to be uncovered. This journey into the heart of hyperluminous infrared galaxies is far from over. Each new observation peels back another layer of complexity, revealing a cosmos more dynamic and interconnected than we ever imagined. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.